It's interesting. The number is going up slowly. Does that, I wonder what that means in terms of like, does Zoom just like let them in slowly, or are people just arriving? I don't
Or everybody is really tired from yesterday.
know. Yeah, I scared them all away yesterday. I should have made sure to say like, and tomorrow, we're going to actually look at the data.
Well, let's give it a few more minutes.
Mm-hmm.
Okay, good morning, everybody. So some people are still arriving, but we can go ahead and start little by little. So thank you very much for joining us today on day 3 of May Institute on Computation and Statistics for Mass Spectrometry and Proteomics. We are very happy to see that you are still around, that we didn't exhaust you in the first 2 days. This is very good news. So we have more to discuss today. Today, Brendan will be focusing on DIA experiments and working with DIA experiments in Skyline. Just a reminder, while everybody is joining, so we have the chat button and the Q&A button. So please use Q&A for anything related to the scientific content, questions, comments, and so on, because our wonderful teaching assistants can manage that much more easily when it is in Q&A. So Ali Marsh is with us today as a teaching assistant, and we may have even more teaching assistants joining us later today. Thank you, Ali, very much for joining us. So other than that, well, let me welcome Brendan back. And Brendan, we look forward to actually looking at some data today. So thank you so much.
Yeah, hello. Welcome back, everyone, or those of you that had the that were brave enough to come back. Still some people dribbling in. I don't want to go too far into things, but yeah, I have some questions again that I would like to ask of people, and just to see how far people got.
So don't forget to turn off your PowerPoint.
Yeah, I'm gonna stop this PowerPoint, and then now I'm gonna start up the one with the questions, because that was a problem yesterday. And let's see, so it's starting this questioning app. Whoops. Yeah, so the starting question is, oh no, that's the last question. I'm sorry. Hang on, don't answer that. I somehow started the slideshow. Okay, so at the beginning of the slideshow, here we go. Whoops. Okay. Is that the first? No, there we go. Okay. So starting out again, same question as yesterday. Did you do the DIA swath tutorial? So people, yesterday it maybe wasn't that clear, but there's a companion swath tutorial that really, if you want to learn DIA and swath, you should do that tutorial. One thing that I realized is, it may be a good idea to switch this up so that instead of starting with teaching the Bruder data, we start with teaching setting up the processing that's done in the DIA swath tutorial with Skyline batch. So that's an exercise for those of you well, everybody should try to do the DIA swath tutorial at some point if you're interested in doing DIA. And then I would say try to go back to that tutorial and set it, go through the process we did yesterday, where you create a template with no data in it, and then you run Skyline batch to do the processing. And that should be possible with that tutorial as well. And then the other thing about those tutorials is they don't use the assay library. So yesterday we used this assay library, and some people asked, well, how do I get that? How do I get one of those? And we're not expecting that a lot of people come to Skyline with an assay library. They're produced by other tools, not Skyline. If you do the DI swath tutorial, that really takes you from ground zero. And we're going to look at that a little bit again today with the CelebSec data, where we start with some search results in a PepXML format, and we're going to go through how to build a library and just sort of natively go through Skyline processing. And the same thing happens in the DIA tutorial. So it's not that common that you have an assay library, and so a little bit awkward that we started with that yesterday, but that's what we had for the Brooder data. Okay, well, good. I'm glad that over half the people who answered have done it, but not, what do we have? We have 69 people. About half the people answered. So oh no, it's less than half the people did it, and most people did not do this. So again, if you want to learn DIA swath, when we do weekly courses, which where we get everybody together for like 6 to 8 hours a day, we sort of force you to do hands-on tutorials by yourself, and then with instructors there to help you, but you do have to sit down and walk through the steps. So do this tutorial if you're interested in DIA. Next question. So yesterday we got far enough that ideally everybody should have been able to do the Brooder Skyline batch processing. So lots of people didn't, it seems. And we'll get to reasons why you maybe didn't. But wow, very few people actually made it all the way through. And maybe it'll be interesting to get more information on why. I even did it on one of my home computers, so I tested out. I have reasonably fast network speeds, but last year we were able to get even somebody from Europe to get through it. So again, about the same 34 people responding. Most people actually did not get through it. So that is unfortunate. So what did you find most helpful yesterday? So assuming at least for those people who attended yesterday, just free answer word, there's going to be a word cloud. Just tell me, what was it, just getting a Skyline intro. And yesterday was just confusing. nothing was in, oh wow, DIA by Skyline. So yeah, for the people that found it confusing and not that helpful, I really have to recommend that you go. Yeah, it's unfortunate that we jump you right in so quickly, because this is the material I'm teaching was previously the capstone of a 2-week class, and you got lots more hands-on time with Skyline. In this case, we're really asking you to get some introduction to Skyline by doing the tutorials. So if it was really challenging yesterday, I would suggest going back and looking at tutorials, looking at some of the intro tutorials. There are actually 2 DIA tutorials. One's very intro, and then the other one is the DIA swath that I've been recommending. The aim is not clear for me. Well, the aim is to get you through what it takes to do large scale DIA processing. So yeah, we're not even the intro to sort of how do you do DIA processing in Skyline is that tutorial. And so since so few people are actually doing it, maybe next year we should just reset this to be much more introductory. But all right, well, there we go. We've got our about our 33 answers again. Sorry for those. Yeah, what do you most hope to learn today? And we could, last year we spent most of the day just looking at the data because that seemed to be what people really wanted to do. And we can again take a poll to see, we're going to look at the data. Yeah, okay, the basics of Skyline first spectral library. That is definitely what we would be doing with the Celebsec data. Evaluation of data, we'll definitely do that. How to check DIA quality, we definitely will do that. Look at data, yeah, that sounds awesome. Let's do it. Command line tools. So command line tools, we're not really gonna be getting too much into the nitty gritty of the command line. I can, I certainly, based on a question, I can show you the command line interface. Skyline batch is using the command line interface. So you've been using Skyline command line. There's no Skyline UI showing up. It's just that it's Skyline batch that's making the command line calls, and you can make them yourself if you're a programmer type. Yeah. Okay. So how to check data quality, spectral library building, make use of libraries, clear aims workflow. Okay. So good. Thanks very much for that feedback. And how was the phase yesterday? So now we get a sense of how many people just thought like, yeah, that was way too fast. And I, too much presented and I didn't really understand you. But yeah, a lot of just right, a little too fast. And that's pretty consistent with last year as well for the people who were following along. It was maybe a little fast. Nobody ever says it's too little, too slow. A little too slow, some people, yeah. So those are the experts, the people who have a lot of, and then the people who just feel like, wow, you're throwing a ton at me. We definitely, that's unfortunate and really, yes, I would agree that I'm starting with material that I would prefer to be teaching at the end of a week-long course and not sort of on day 2 and as Lindsay and Sue pointed out, that they presented in 3 hours the material that previously at the May Institute they had 2.5 days to present. And so yeah, this is a little bit hyphenated. I'm glad that we're getting up to 40 people now responding. Thanks for that. Yeah, so then this is the, okay, so how much progress have you made? So some people said they finished running Skyline batch, but did you actually run all the way through MS stats, or, what happened? Get a little bit more information on what happened to everybody. And let's see, ran through Skyline, but MS stats failed. Okay, so that's unfortunate, but maybe today or later we can help out the people who are having trouble running MS stats. Got lost trying to, so yesterday when we were doing the template, I guess people fell behind and I didn't make it clear enough how you could just grab the template off the website. So yeah, I should have made that clearer. So file download failed. That's unfortunate too. Yeah, so I see, I have been thinking like this is going to be, yeah, I'm thinking about like, what if we go back to in person, do I just show up with hard drives for everybody? Or like, because there's no way if we're sitting in Northeastern that everybody's going to be able to download the data. So the hope was that, with spread out over a whole night or two, with people downloading the data to many different institutions, that we would be able to get everybody downloading the data. But so we got 20, so we got about 10 people who actually finished running everything. and about 10 people who got through that and Skyline and then failed MS stats. And then people who sort of created the template yesterday, but just didn't run Skyline batch. And a lot of people who, unfortunately, I guess a third of the people who just had trouble creating the template. So we can go through creating another template today, or we can spend all of our time looking at data. We'll see. And that is the end of my questions. And so let's move on to let's see what I don't have enough space on my computer to run CelebSec on. Yeah, okay. Yes, so yeah, we're going to start definitely right now. We're not going to jump into the CelebSec data just yet. We're going to go back and look at how the processing looked. So I'm actually going to switch to so first we're just going to look at Skyline batch and what successful processing looks like in Skyline batch. So I'm going to switch to not my normal work computer that we were doing most of our work on yesterday, but a very large computer. But even this computer is 5 years old and we're in the process of replacing it. So visiting the Aebersold lab, oops, I gotta get the password. Visiting the Aebersold lab, I was made aware that they had this really huge computer, and I said, we need one of those too. And so just because people were complaining that on these very large computers, Skyline was not making complete use of all of this expensive hardware, and it was running slower than they would like. And so we did a lot of work to make sure that Skyline could fully use a computer like this, which if I bring up the task manager, oops. Oh, it's not letting me bring up the task. Oh, maybe. Okay, so if I bring up the task manager, you can see that this has got 24 cores and it's 48 hyper-threaded. So to get this, and you can see the memory is 192 gigabytes. And so this is a big server computer that a lot of people can use together, but it also, right now, you can see it's just sitting idly. So our goal was to make Skyline use this efficiently, and then, at this point it does, and we're gonna get a 5-year upgrade on this computer and then play around with how, can we make things even faster on a computer, a modern computer like this. But so this is Skyline batch, with the CFG files or the BFG files, Skyline BCFG, the BCFG files, the batch config files loaded into it. And then these are the logs. And so Skyline keeps, you can see Skyline keeps a list of logs. Every processing that I've done here since installing Skyline batch, I've got a log for, and I can get to it. If I switch to the log, I could be looking at, here's the current log. Well, I haven't started any processing this morning, but also, there are these logs, and this, I think, that's a CelebSec processing. So what I'm looking for is a Bruderer processing. So this, I did them in separate operations, and I get a batch file for pretty much every time I click this run button. And then I can actually, you'll see that if I switch to something where I ran MS stats, which I think would be here, it says log truncated. So the log is, for MS stats is so long that it gets truncated. You can see it took 2 hours to do the MS stats processing for, this is probably our largest data set. But you can always get to all the logs by clicking open folder. You can delete logs if you're like, I don't really want to save that one. But yeah, so you can see some of the really big MS stats log files here, and then you can use, and this comes up selecting the one that I had selected. So I can just click on that, and then I can use either of these two editors are my favorite editors, Notepad++, is just a really great editor, all around editor, and EM editor is like, can edit anything. It edits huge files. So if you're going to be looking at really, and these are not huge files, but if you wanted to look at something that's like multiple gigabytes or something like that, EM editor is a great choice. But I can then, I can open up this whole log file pretty easily, and you can see it's running MS stats, and this is the log for MS stats. So that's a way to get to complete log. Let us go back to, so highly recommended Notepad++ and EM editor. And then let's go back to the processing. Oh, I thought that was it. Darn. We're looking for that's the CelebSec, and here's the Bruder processing. So this is ideally what our processing should have looked like. In this case, so in this case it finds 24. This is actually doing the download as well. So you can see that it says, hey, there are 24 raw data files I need to download. So first it just goes through downloading them from Panorama. And you can see in this case, it makes it through all 24, which apparently not everybody was able to do last night. I'd be interested in maybe if people could share their logs later today, maybe we could look at like how is it failing downloading, how long is it taking to download. This computer is probably really quite close to Panorama, so it downloads very quickly. But so then we start up the actual Skyline processing, and you can see that these are the Skyline command line commands that Skyline batch is sending to Skyline. So first it just we print out the version number by going -- version to Skyline, and then we create this batch in a temp file, which you could go look at if something fails, and then but what's in the batch temp file is here. And so yeah, so this is all printing out like, hey, I'm going to run these commands on Skyline. And then now the commands start running on Skyline, and you can see it opens a file. It opens, and this is the template file. First it saves that file to this name, I guess. So it gives it a new name with the full location, same as where
Brendan,
we're saying.
can I interrupt you for a second? A whole bunch of questions here in the Q&A.
Whole bunch of questions.
So
when we refine the number of transitions, what does the auto select all do? Why do we only check the transition option only? Okay, so that's a good question. So I showed you that we wanted 6 transitions per peptide, and in the library they had like sometimes they had 10, sometimes they had more, and we wanted to set it back to 6. So it's nice that the library contained more. That gave us more options and more of the spectrum. We didn't get a raw spectrum, but we got some larger set of things. And so we didn't want to actually extract chromatograms for all of those. And so that's where we had set our settings to say we only want 6 transitions. But then what happened when we import an assay library that has 10, 12 transitions, Skyline goes, oh, well, that's what you really want. And so we had to go back to the refinement and say, no, choose just choose the transitions that I told you to choose. And then the other thing we did was we said, okay, there may even be some precursors here that don't have 6. We also wanted to say we wanted 6 and only 6. And so we reapplied the limit by checking the transitions checkbox. We reapplied the limit that said, hey, we want 6. We want to not have 10 or 12. We don't want to have more than 6. And by restating that we wanted only 6, that would get rid of precursors that had less than 6. So after we did that operation, we would have all of our precursors would have a transition count of 6. So that's what that refinement step was doing. Nice question, thank you. And then can we get a little more in-depth info about the files we're loading and why? That was unclear to me yesterday. I get that raw files are the spectra, but a CSV can have anything. Okay. So, and then there's BCFG, BLIB, skills, SLC. Yeah, so a bunch of these. So the BCFG is a configuration for Skyline batch. And then the rest of these files listed are part of a Skyline project. And I can tell you what each one of what the function of each one is. And yes, the CSV, in this case, it's something called an assay library. And there are actually multiple formats of an assay library. It's not a highly constrained thing. I used to call it it's a transition list. It's just like another transition list, but an assay library is a transition list that also contains relative ion abundance and the normalized retention time, the IRT value. So that's what we call an assay library. And when you say import an assay library, then Skyline knows to look for things. And that, in that case, that was an assay library exported from the tool Spectronaut. So we also have seen, assay libraries exported from OpenSwath. There's a bunch of tools that produce this assay library format. It's something that the Aerosol lab came up with. So yes, I agree. Just having the document type CSV, yeah, it could be anything. So there's lots of formats, and Skyline, in terms of importing targets, Skyline has often worked with CSVs because that's actually what a lot of the instruments accept is, you import a transition list as a CSV. So Skyline is very flexible at accepting a CSV to populate it with targets. And then, yeah, let me then go to, here we are in Celebsec. So then there's question about, okay, there's Sky, Skid, Skill. So there's a bunch of, so the Skyline is the Skyline document. That's the main thing. The Skid will appear once you have done chromatogram extraction. So it's the chromatogram data and the peaks data, and it's a binary file. This is an XML file. And then lastly, this is an XML file, and this is the skill is the log. It's the Skyline log. So these three are sort of a pair for just about any Skyline project with data imported into it, as long as you're doing audit logging. And then also pointed out is that there's potentially this .blib, which is that's Skyline spectral library format. It's a binary SQLite format. IRTDB is also a binary SQLite format, and that's where we store IRTs. And then SLC is a Skyline library cache. So this is really down in the details level. It's something that it's not necessary. You could delete it at any time, but then it's just going to take longer for Skyline to load the library, because you can see that the library is almost a megabyte or a gigabyte here. So this is almost a gigabyte library, and with 12 meg, we can really efficiently express it. And so Skyline can load it very immediately. So that's what these files are. There's other types of files you could use. And I talk about a Skyline document, but people have said you should talk about a Skyline project. Downloading files from Panorama takes ages. Celebsec data was been downloading for almost 24 hours and still in progress. Is it an issue of Panorama Web? So I don't think it's an issue of Panorama Web. It may be if everybody in the class is trying to download it. Last year, when fewer people were trying to download all their data off of Panorama Web, we ended up finding that Panorama Web was one of the fastest downloads. We originally tried to have people download from the original data sources, which are Pride and Peptide Atlas. And Peptide Atlas in particular was quite slow for anybody in Europe. And we found that we got much better performance with Panorama Web. So it's just an interesting thing for me to try. Okay, 50 people try to get some data. And I'm sorry that it hasn't worked as smoothly as as we would like. I don't have a way of giving you all a flash drive or a hard drive, or one of the things when we did the DIA course in ETH, it was really wonderful. They all, they had these virtual machines, and everybody would just sit down, log into a virtual machine, and everybody had exactly the same thing, all the same files. So we're still playing around with this. I'm sorry that it hasn't gone as smoothly as we'd hoped. Let's see. Runtime 0 completed. MS stats.
I think Ali is helping with this one.
Oh, okay. All right, great. So we're all set. Let's keep going. So if we're looking at, so we're going through the Skyline batch, what it's doing. So it's now here, it's opening so it's copied the template file to a new file, and then it opens it. And then, or no, it just saves it. We open the template file, we save it. And then to the saved file, we say, okay, we're going to import some raw data. It's 24 files. And on this computer, because it's got so many processors, it's able to do 12 at a time. And you can see we start at 948 and doing 12 at a time, where it's done done importing in 13 minutes. So pretty fast processing, parallel processing. Then we join, this creates a bunch of little SCID files, and then it joins them all. And so you can see there's a little bit of, maybe just another minute of time, less than a minute, where it joins all the files into one SCID file. So that we saw that SCID file, that's the chromatogram file. So it's processed everything, gotten all the peaks and the chromatograms, and putting them into a single file. Then it updates peak statistics, and then it begins to build the M-profit model that we asked it to do. It goes through several iterations to get to a optimal 1% FDR. And then this is a really important place to look when you're doing this kind of processing. This is the scoring model, and what you'd like to see is you'd like to see everything represented here. So these are all the scores, and there could be scores that say no, we're not not correct, and you'd like to see the percentages all positive, which they are. If anything with a negative percentage, I think means like, hey, this is going the wrong direction. So we'd like to see everything. You can, and we'll look at the model in Skyline. It's much more visual, but yeah. So I look here and go, oh, okay, great. The retention time difference is providing some benefit, not a ton. It like sometimes if the retention time prediction is really good, you see this up in the over 10% to 20%. Library intensity, you always expect that to be a pretty strong score. So the fact that it's 36% of the score is good. These other scores, and then coelution count is also usually a pretty strong score, so it's good to see those. And then very hit or miss on this data quality, whether or not these other things like signal to noise and mass error provide much benefit. But this is when I get down to here and see these sort of, here we got 500,000 peaks at 1% FDR, and we got, pretty nice model. That's very, positive, and makes you, you're like, okay, great, things processed well. And we're going to open the document up in Skyline soon, but I wanted to show you this log. This log, you can, again, if you go open folder, you come up and that log will be selected. And if you wanted to copy it and submit it with your paper, hey, here's the log of how I processed everything, you could do that. And then now we start writing a report. This is the MS Stats Input Plus report. And in this case, that's all I did. I did not run MS Stats. So you can, we created 2 configs yesterday, one with MS Stats and one without, and this would be running that config. And then you can see, I showed you another log where I actually ran MS Stats, and that's a much longer log. But yeah, so now let's go back to my other computer, where I've tried to set it up how, sort of how I hoped that you would end up. So if you were doing yesterday, you have this Brooder 2022 MS stats, you have these things, and my hope was that everybody would have actually been able to, or like a majority of you would have been able to finish at least the first Brooder and then maybe do the MS stats as well. Today we're on to CelebSec, and what time will tell whether or not we actually get to processing these. But this is what Skyline batch would look like if you had simply followed the instructions of so can we bring up so here we got to do.
And Brendan, there's a couple more questions.
Okay, a couple more questions. I will get back to those. So if we go to the May Institute today, the document that we're following along on and is here, and we ask that you go to this data set and download this BCFG file. So here we'll go to that data set. So this is another data set on Panorama Public. It's really very well documented. Hopefully after this class, if you actually learn the objectives of this class, which I guess people are saying I didn't state clearly enough, you would be able to come to this page, totally understand it, and you could reprocess the data on your machine and feel like, wow, okay, I got from here are all the templates, or no, this is the template down here, the less than a gigabyte, 863 megabytes, that's the template. And then these are the process data. And you should be able to, come to something like this and reprocess the data at a bare minimum. And if you read more deeply and did more of the tutorials, ideally, more and more people would be able to submit as this, so that anybody could walk up to your Panorama Public submission with your paper. This is with Ali's paper. You can see the MCP 2015. Oh no, that's not the paper is well, I don't know. Oh, where is the paper? There's the paper, Skyline batch. So here's the paper. This is information about the paper, and this was submitted with her paper. And so we would ideally like to see as many people as possible submitting like this with full information on how to reproduce the data processing. But all we were asking last night is that you download this BCFG file, like just clicking on it, and there I've got a second copy of it, and then you open it up, and then it would just come in here. So that was the hope, and then that would mean that for people who did or do eventually successfully get through the stuff that that I'm suggesting here, you would have something like this NEU 2022 with a Brooder folder and a CelebSec folder, and I've also got the process folders. But your CelebSec folder now would look like this, where actually there's two data sets here, and I'll explain this later. But this is a replicate data set, and this is an osmotic shock data set. So two different experiments with the same, in the same environment, and that we then have a certain amount of processing that we would like to do. This is the template file, and we may or may not go through how to create one of these template files with the CelebSec data ourselves. But if I drill in here, you can see that this template file has a .sky, which again, that's the main Skyline project document. Sky.view is just where the windows and the selection were. It's just, again, this is something that could be deleted, but it saves how the Skyline file looks in your in Skyline. And then this is the skill file is the audit log explaining how we created this Skyline document. And then this is the spectral library and an IRT library. And it's not, sometimes the IRT information can be stored in the blib file. All right, so that's what ideally everybody would have, and everybody would have a Skyline batch that looks like that. But now let's go back to the Brooder process. So everybody would also ideally have this Bruder processed. So that, they've got the Bruder 2022 document that's the template that it seems like many people, I mean, I'm sure it's quite hard to follow along, and certainly very hard for anybody who doesn't have two monitors. But following along with me yesterday was probably challenging, and it's much easier to be in a room with people who can raise their hands, or you can ask them, are you done? Or you can even walk behind them and look at all their computers. And so it's challenging to keep everybody following along in this setting. But this is the template that I created yesterday. And if you were able to follow the steps, you would have something like this. And then this is the raw data library. These are all folders that we used yesterday. And then finally, here is the fully processed file with MS Stats run. All the MS Stats information is in, these files. This is the report we exported, MS Stats Input Plus, which was the input to MS Stats, and it then created all these. Before opening Skyline, I found this, there's a bunch of different plots here, but I found this volcano plot, which I thought was pretty interesting. It's a set of volcano plots actually, but I think this is one of the small, you can see some of these are 150 megabytes in size. So this is one of the smaller ones. And, I liked the volcano plots when I opened it up. So here I'm opening up, it's actually went right back to where I was when I was looking at it. So, here there's just two things, and we don't know what they are, but two things that are showing up highly, one upregulated, one down-regulated between S1 and S2. And as we go, yeah, it's strange that S3 and S2, I don't know, is that real? Anyway, maybe it's not, because maybe these are just points that force the plot to have this scale. I don't know. We don't have Mina here, but it looks like the true points that are showing up here. So again, in the osmotic shock experiment, it's a time course. So S1 and S2 are expected to be highly similar. So this is not a surprising volcano plot. Like, we're not expecting a lot of difference. And then S1 and S3, we're starting to see a little bit of difference. Yeah, I think these spots are not real things. They just somehow define the extent of the graph. And then S2 and S3, again, very similar in the time course. Anytime we're comparing points that are very close together, they're similar in the time course. And then, S1 and S4 is further apart, and we're starting to see more things show up. So yeah, I think, and then, S1 and S5 is really far apart. And so now we're seeing, a bunch of different proteins. So in terms of, and then I think, what do we get to? S1 and S6. So I think what's the 7? So there's 7. So, and as you see, S6 and S7 have fewer differences. The further we get apart, the more differences we see. So that one of the furthest apart would be S1 and S7. We see lots of big differences. And they're labeled with the protein names. So we could go into Skyline and search for some of those. So let's now open up, go here. So that's kind of, I enjoyed looking at that. Thought that's a really informative set of plots. Let's go ahead and double click on this Bruder22.sky. And this may take a second to upload because it's already gotten pretty big or to open. It's already gotten pretty big with its set of runs. Let's see. Quick question. Should we just use R 4.0.3? How about latest version? So yeah, you should just use 4.0.3. We had some issues with the latest version getting MS Stats installed. On my machine, those were resolved by, I got all the latest tools, and I was able to build MS Stats in 4.2, which is the latest version, but I had to be an administrator. So I had to run RStudio as an administrator. How important is intensity? Was doing tutorial and noticed I was getting a lower intensity score, a negative score. Intensity, yeah, intensity is not often, like, yeah, intensity was an early original score, but it is pretty, it turns out not to be that good a score. And so it used the original mProfit paper said that they trained mProfit based on the intensity score. And so did we. When we started mProfit. We now train mProfit based on the Skyline default score, which is not very, doesn't give intensity a whole lot of weight. So it turned out that intensity score is not consistently a great score, and yeah, sometimes it shows up as negative. There's more signal on the decoys than there is on the targets. So I answered that one live. And then trying to confirm what files are needed to successfully run in Skyline batch, Skyline template, raw data, and assay library. Anything else needed? So you don't technically need an assay library. You just, to run it successfully in Skyline batch, you need a Skyline template and raw data. And I would say, go back and do that DIA swath tutorial, and then try to do it as just creating a template, and then import the data later using Skyline batch. And that's a good exercise for Skyline batch. But yeah, the assay library is totally, that is a way, like, you need to create a template, and in the template, you need to provide what you're targeting. And one way of doing that is an assay library. It's not actually the typical way. It was just the way that in order to reanalyze that paper data, that's what I needed. So I can see that that's confusing. And so maybe next time I teach this, I'm gonna stop using the Bruder data. It's a really nice data set, but everybody gets confused because I'm starting with something that is not that typical. Is it okay to use Skyline daily for these tutorials? Yeah, it's really okay. I wanted, last year we did use Skyline daily for everything. One thing that I pointed out is if you're using Skyline daily, then in these configurations, you can see there's a Skyline tab, and you want to make sure, I don't even have Skyline daily installed on this computer, but you would need to check that to say, hey, I'm going to process everything with Skyline daily. But totally okay to use Skyline daily. There shouldn't be anything broken. Okay, so I'm going to keep going. So here now Skyline is open with everything processed, and right at the top we try to put the IRTs right at the top, because that's pretty informative. And you should, your IRTs will have repeatably the same color, so you'll be able to look at this and go like, oh yeah, great, my IRTs all look strong and showed up. And then the next thing to do, and so we'll start with just a little bit of like, okay, we saw things that made us feel good in the log file, but let's do some analysis here, some review of, and that was one of the things somebody said they wanted to learn was, how do I assess the data? So before we're ready, we ran through and ran MS Stats, but generally I would say, like, don't run MS Stats until you've done some assessment of whether or not you actually process the data ideally. And in this case, I'm going to say you process the data pretty ideally, because I did all the work to figure out what was the ideal setup for this data, but it may take some time, it may take a little bit more effort on your own data. So let's go to view retention times replicate comparison. And this gives us a view into, how reproducible is the retention time. And these are the Irt peptides. So ideally, we just like to see a straight line across. I'm going to take this. Let's see. I like putting this with a lot of vertical height, because it gives me, more ability to see some variance even in this. So this is totally acceptable variance in retention time. One thing we could check is, we've imported these based on their names. So they're ordered by their names, sample 1, 1, 2, replicate. But ideally, I would say that actually we'd like to see that we hope that they were not acquired in this order for reasons of randomization and blocking that Olga will probably explain at some point in this course if you show up for her statistical lectures. So let's go right click and order by acquired time. So it's turned out that acquired time is an incredibly important value in mass spectrometry. And if you don't randomize, then your acquisition order can become a confounding variable in your statistics. So having insight into acquired time and the order and in which things were acquired is really has become very important. And so Skyline has it as a primary value that allows you to order a lot of things by and look at very easily. So
Brendan, there's a couple of questions about Irt peptides. If you could repeat what they are and how they.
So the Irt peptides are sort of retention time anchors. They are the peptides by which we detect these peptides, and then they allow us to predict where all the other peptides are going to come out, right? So if numerically, if we know that a peptide usually comes out halfway between this pink one and this blue one, then we can, once we know, hey, the pink one came out at 50 and the blue one came out at, or the blue one came out at 45 and the pink one came out at 50. Well, then we expect around 43, we expect our peptide to come out. So that's these Irt peptides. They're injected in this case, they're injected into the sample. We can also use endogenous peptides for Irt standards. These are the anchor peptides that predict where every other peptide in our sample is coming out. You see, we have 50,000 peptides and we can predict them all with just these 11. But it's very important that they look like this, that they're very reproducibly, they come out very reproducibly. And you can, so this is the acquired order. Sometimes you'll see some slippage, and we can see that more clearly if we select each one individually. So I would say, like, there's no big, if suddenly you saw the blue one appearing up here, that would be a problem, right? But there's everything's appearing in the same order relatively. You can see here's a bit of a jump in this one here, but all of them jump. They all kind of move later. So they are relative to each other. They're doing quite well, but we can also click on an individual one and get some sense of, this gives us the retention time range, is expanded to just what this one peptide. And you can see it's really over, we have 3 minutes of time here, and all of the retention times are basically within a minute or so of each other. So then we can keep doing this. And I usually, it is a little surprising to me that these are not just really overlapping. You can maybe see there's some drift toward things coming out earlier and earlier. That's a pretty common thing in mass spectrometry. So you can see that if you let your eye sort of draw a line through these points, and maybe it's easy. So this is this vertical thing represents the peak that we're looking down on the tops of all the peaks. And then there's this is the apex of the peak. So you want to see it's good when you see these all line up. That's an indication of coelution. So this is looking like really nice data. And then you can still see, okay, the peaks are less than a minute wide, or about a minute wide or less. So that's good too. But we can also right click here and switch to a value that is just the retention time. And then now we get a line graph. And maybe that makes it even easier to sort of see, like, oh yeah, it's like kind of the times are drifting. And that's why this is so important, is that, if we chose a specific time in this gradient to look for our peaks, we would, we would have, if we just said, okay, I always expect this thing to come out. I saw it once at 55.5, and so I always expect it to come out at 55.5. Well, then by the end of your run, it's kind of, it's starting to come out at more like 54. So yeah, that's what and so we can take another way, we can use another way of looking at this and assessing how we feel about this. But this first look of just, hey, do these look pretty straight across? Yeah, they look fine. When I see a jog in the line, it's a sort of consistent jog. This is all like, really good looking IRT data. So let's also get a better look at how the prediction is working. So here we can go to regression, score to run. So the IRT is considered a score. And then this gives us some insight into what Skyline is doing. Skyline has this, the predictor is given this. It's got an R with the points of 0.9958, so really good. And at this point, you can see some things that are on the y-axis, and those are things that were just not detected. But we can play with what points are plotted here too. So we can go to points, and we can say, well, what if I only take the things that were within 1% FDR, and on the things that were on the 0 go away. We maybe get in a little closer, and we'll look at this again in a more informative plot. But a really good set of points to look at are just the standards. So these are the IRT standards. We can see again that the predictor. So the predictor comes from running a linear regression on the standards, and we can see that we have an R of 0.998. Now, another thing I'm going to do here is right click, and we can decide it's already on single replicates. So that is one of the more, we could do all, but in this case, we generally would like to see, well, if I go through each one of these, I'm really not seeing very much variance in the predictor or the predictors. Y-intercept is probably changing sometimes a little bit, but I get really nice prediction, and the Irt peptides are very close to that line. Another way of looking at these data is to actually plot the residuals. And so now we're just plotting. So now it looks, whoa, like they're all over the place. I thought they were right on the line, but they're all over the place. But really, they're pretty much within 2 minutes of the line. So I will admit that, yeah, like some data sets, these residuals are smaller, and you will see them all being within 1 minute of the line. But this is still totally fine. I mean, we ended up giving ourselves 5 minutes. So now let's switch to the full set of points. We'll go with the 1% FDR again, and this will give us a sense of, here you go. This is, and what looked incredibly linear is maybe not so linear, right? There's like some sort of effects that are happening here, and that's just a difference. Like they probably collected these IRT values on a very different gradient, probably a different column. So the IRT values were come from the DDA. So we said that they ran DDA runs. They come from the DDA runs. And so, but still there, we extracted out to 5 minutes, and you can see that everything is way within 5 minutes. So that's one of our biggest takeaways is like, hey, the 5 minute range. So if I go to settings, transition settings, in full scan, we said, hey, we're going to allow 5 minutes within the prediction. And so we can see that's plenty of space, right? There's no evidence that we're that these peptides are being detected out that far away from our predictions. So our predictions are still quite good. This in data where you would get a, so we saw in the model, the mProfit model, that retention time was not a particularly strong score. It was like 5%. It would be stronger if there wasn't all this, these extra variance, systematic variance in these numbers. So we also have the ability to look at what the decoys look like. So, how do our targets compare to our decoys? And oh yeah, so we have to zoom in here because in this case, we have no way of saying within 1% FDR. So we still have this line of things are things that just were not detected. They may have had no signal, but you can see it's different. There is still, maybe some so sorry, I just cut out there. But yeah, this may just be that the scoring model is favoring things close to this IRT value because that's clearly beneficial for the targets. But yeah, we see things spread out all the way to the limit of 5. So these are our decoys, and we expect them to behave more like this than the target. So that's all good. So I'm going to switch Pat to there. So that's it for retention time. There's this weird, curving artifact going on. It's not, we would rather see everything just clustered around 0, but still not a big problem. So the next thing we can look at is, similarly, we made some decisions about the mass range that we were willing to accept. So if we go back to these transition settings, two really important values that we chose were, what range of the chromatogram are we willing to consider? And we gave it 5 minutes, or 5 minutes on each side, so 10 minutes. And then we have this mass accuracy of 15 ppm. So actually, let me just show you how. So now we zoom in on some real, a particular real data point. Data looks really beautiful, I think. But you can see that when I'm out at the full range, I've extracted only 10 minutes of chromatogram. So this is 77 or 79 to 89, right? And that's what that 10-minute window, that plus or minus 5, got me. Here's the prediction. Skyline is graphing like this is where I expected the thing to show up, and you can see it showed up very close to it. And then also Skyline shows you this red spot. This is where it is on, in the retention time plot. So all these plots are very tied together, and you can like click on, any point in here and go like, well, what about this one? And that one does not look as nice, even though it is not that far from its predicted retention time. Yeah, so not all the data looks as nice. This is maybe, this actually, I would say probably this is showing me that the mProfit model did a worse job at predicting than the Skyline default. So the Skyline default chose this kind of purple, and the mProfit model said, nah, I think it's this thing. So that is some indication of that. But statistically, right, so I guarantee you look at any tool with Skyline, and you look at, any model, and you're going to see things where you're like, hey, it's making mistakes. And that's, statistics is not perfect. Its goal is to detect signal in the noise. And, we can go to, we can see many other cases where Skyline with mProfit is doing a great job of picking really nice peaks. In our case, it'll tend to be these green ones that will tend to be really nice data. you know, yellow and red kind of say, you know, maybe there's some more thought to be given. But anyway, so let's go to the mass errors. Go back to this is, we're still just, you know, you can eventually you can just start looking at plots like this, and but I would say first it's better to look at some of your overall statistics. So let's take a look at this mass error histogram. And here we can see that, wow, actually, that's really interesting. I forgot about this. So the mass error is 10 ppm, and it's got a 4. Is this what am I looking at? Yeah, points, targets, 1% FDR, maybe. Yeah, so it's and it's per replicate. So I think this is actually, let's go ahead and switch to replicates all. And then you see it kind of, there is still, you know, a mass error of 6 with a standard deviation of 4. And you can see one thing we can see is that it's not real. It doesn't look like there's a whole lot out at 15 that we're missing out on, right? The distribution is still pretty much covered by 15, even though the mean is 6 and the standard deviation is 4. And my rule of thumb is to take this number 6 and then multiply this number. So I would say that probably I would have recommended a 20 ppm window, but I'm neither am I seeing a real big problem with the fact that we chose a 15-minute window. But what we just saw is sometimes when you see a really wide you know, curve like this, or sometimes I've even seen like it end up looking like it has two humps, then what you want to do is go back to single, because what we're going to see is that there's retention time shift over these runs. And so now what may be, I'm going to close this regression plot because I can see it painting in the background. And so now we've seen like, oh, there is some retention time shifting going on. That's kind of, or some mass error shifting going on. And that's probably why mass error is not a great score. So again, when we look at the model, I'll look at the model again and in a second, and we'll see that mass error is not a great score. If it's centered right around 0 and very you know, low standard deviation, then mass error will become a much stronger score. But let's go and look at mass error's replicate comparison. And here we can see, yeah, okay, there it is. This is by transition, but you can see that over time, and this is ordered by acquired time. So they had mass error slippage on their instrument from around 3 ppm to around 10 ppm. So ideally, you don't want to have this. And that's what Panorama Auto QC would do a great job at helping you know when this is happening to you, and then you would go and recalibrate. And probably ideally you wouldn't even start a run with a 3 ppm mass error. We like to keep ours, you know, within 2. But yeah, that's the, you know, it's still not a problem. It's not like, oh, this is a terrible problem for this data, but something to keep in mind, especially when we're, you know, choosing the transition settings. And yeah, this is the kind of thing that we're trying to make it easier and easier for you to see in Skyline. And there's countless times people have sent me their data, and within 15 minutes I can be telling them stuff about their data that they didn't even realize if they're not adept at using Skyline. So that's a quick look at the mass errors. Nothing, you know, nothing to be too worried about. I mean, we might try redoing this with a 20 ppm mass error if we think that we're losing stuff out here, because we definitely see this long tail going this direction and not so much going this direction. So maybe the 15 is kind of cutting things off. I don't know. But again, we don't really feel like we have a big problem there. And then let's see. So let's now go to the refine, reintegrate, which is where we can see our M profit model.
Brendan,
Yeah.
before continuing, can you take a quick look at the Q&A? We have some good questions.
Okay.
There.
Okay, good. I will stop. I do. So yeah, I'm trying to get through a set of things that are sort of checking the health of the processing. So far, we've gotten through retention time and mass error. Okay. Can IRT predict RTs for peptides with PTMs? Absolutely. The IRT library, actually, if we go to settings, peptide settings, here is the IRT predictor it's under prediction, and it just got automatically created when we imported that assay library. But if we go to edit current, we can see it. And then you can see that there are these, this is just specifying the cysteine modification, which is not a PTM, but a chemically applied label. But we should be able to see like methionine oxidation and let me open this up a little wider. But yes, you can specify these mass shifts. Where's the methionine oxidation? I'm seeing mostly. But yeah, every modification in our document is encoded here. And yes, it's very important to be able to do PTMs because often, methionine oxidation would actually change the retention time of the peptide. So this is how they get specified. Oh, here's the methionine oxidation, M plus 15.99. So that's a PTM. And I don't know if I can, let's see. If I select this, can I sort these? Yeah, okay. So then we don't, okay. We only have it's sorted away from me. Okay, anyway, this is not, that grid is not very good for exploring this, but yes, definitely you can do IRT for PTMs, and it's actually really important. I'm wondering if I missed some key step importing spectral library to visualize my samples in Skyline. Thanks and apologies. So if you didn't get through the processing, so that not that many people said they got through the processing, then you won't be able to see these data. So the data were imported by Skyline batch, right? So we created a template with no data in it, and then we ran Skyline batch to do the data import. And one of the powerful things is we could have actually set up Skyline batch to so here's where we specified the processing for Skyline batch, and in these settings we could have given it a set of like, hey, I want to do I want to do 5 ppm, 10 ppm, 15 ppm, and 20 ppm. You could have set up 4 different processing steps, and Skyline would have processed it in each way, and you'd have a separate document for each one. So you could start out like that, and I did analyses like that. But yeah, if you didn't actually get through the Skyline batch, then your data is not in a Skyline document, and I'm guessing that's the confusion there. What we expect to see in mass error histogram. So in mass error histogram, like, I always like to think about what would I like to see if mass spectrometers were perfect. So if I go to view mass errors histogram, if mass spectrometers were perfect, I would like to see this all lined up at 0. Like I would just like to see one spike, 0. And if they were pretty, and if it were sort of the best possible mass spectrometer performance that I have seen, they would still, the mean would be 0 and the standard deviation would be like 1 or 2, right? And so this has a little bit wider standard deviation, closer to 3 or 3.5 or 4, and the mean is never gets closer than 2, and gets as far away as 10. So that's not ideal. But yeah, the ideal would be just one big thing at 0, and then a narrower distribution centered around 0 is the next best thing. Another thing I didn't point out is that you can also look at the 2D histogram. You can either right click on the plot to bring that up, or you can go to view mass errors 2D histogram, and that can be useful for checking, like, well, okay, I can see that they're not centered around 0, but is there any other artifacts? So over time, not really seeing that the mass error is drifting over time in my gradient. And then another important one is x-axis mass to charge. So is there, maybe there's a little bit of a wiggle, but I have seen ones that actually have quite a bit of curvature. So if it, poorly calibrated mass errors may actually, and you can get even a better, I like to look at this graph in log scale, which gives me, more a bigger range where I see the most intense things. And yeah, see, but this is a fine line. There's no other artifact in the mass errors, but that can be interesting to look at. Instead of just a plain histogram, you can miss stuff. And again, the more that this has a weird shape, the more you want to do things like make sure you're on single replicate, take a look at the, at the 2D histogram, because that can cause a weird shape. Yeah, if you ever look at this histogram and you see it's like bimodal, then there's something else going on. All right. Is there a place in the data that shows which MS platform the data was acquired on? Yeah, so like everything, just about everything we know about the data, it's definitely in the Skyline document if you opened up the text of the Skyline document, and we can do that in a second if you want. But the most powerful place to get at just everything you could ever want in Skyline is this document grid. So it's tabular format, and it shows us, yeah, actually, this is interesting. There's no condition here. There's just bioreplicate. So that's interesting to me. But I would have expected to see condition, which are probably really just the same as bioreplicate. And so we got the volcano plots we were interested in. But so this is the document grid. I opened it up yesterday, so it's already set to replicates. Could be set to proteins, and then this would be my full list of 3,800 proteins. There's a lot of different ways to look at the data, and it's completely customizable. So we can do replicates, and then we can go to customize the report. And then if we expand replicates and expand files, then we actually even have an instrument serial number. Let's see, do we have any sort of, yeah, we don't actually. Yeah, that's a great thing to add here, is like, what is the instrument type? We can definitely get some insight into it from by the path, right? That can help us know whether we were looking at WIF files or looking at raw data files or .d directories or something. But yeah, actually we do know the instrument type, or we can. It's very accessible to us. So that's a great suggestion. Thank you. We will add that very soon, but that would be the place to find it. And once it's added, you would just go customize report, expand replicates, expand files, and then you would be able to say, oh, this file was generated by this machine type. It's also possible that, so we have this data is uploaded to Panorama, right? So here, that's the brooder data. That's the SlabSec data. So this, we uploaded process data. So this is the process file uploaded to Panorama. And so if I click on this, I should get to that in Panorama. And so it tells me, pretty much the same thing, 24 replicates. So this is a process set of things. And yeah, so this tells me the instrument name, at least. Yeah. That's, what is this? Oh, so here, Exactive series slot 1 is the instrument serial number. That's interesting. But anyway, so yes, instrument is Q Exactive right here. So so yeah, clearly Skyline has the information. It's not currently being displayed in the document grid where I expect it. You can open the Skyline document in a text editor. So if we go to the processed here, so the Skyline document is text, it's XML. And I can use this EM editor because this is over 1 gigabyte. And then at the top, I can see all the things that were imported. And here you can see the model and the ion source. Yeah, I'm surprised that we don't put all this in the document grid. So that's a great suggestion, and you can expect that in a Skyline Daily very soon. Thanks for pointing that out. Is this QA log going to be available later? Yes. Look at the doc from yesterday, and the QA log was not posted there. Oh yeah, sorry. Yes. I hope we can. How does that? Is Olga still here? Is anybody still here? We should be able to get yeah, Olga's going to answer and so ideally we will be posting the QA log at the end. I don't know. There's also some sort of voice to text and transcript, but these questions that I'm asking live, I'm not sure how they end up in the QA log with the live answers. Or at least you would like a time at which I answered them live so that you could get to them. Okay, so let's, no more questions. Yeah, I'm still here, Mark Wingert. Okay, so let's keep going. I'm gonna close this down. So we're in Skyline. We're still kind of looking at the health of the processing, which so far looks pretty good. There's, we can see actually, since I ordered by acquired time, I'm gonna pop this out. If I double click on the title, it'll just pop out, and I'll make it as wide as possible. And then change here. And so this is ordered by acquired time. And we can see that this is exactly what we'd like to see. And I know, I think Olga may have advised them on this. We see each replicate is a full set of measurements. So this is called blocking, and Olga will explain that later. And then, so and one of the things that it means is if my mass spectrometer dies in the middle of this set of runs, I still have 2 complete sets. Whereas if I'm doing randomization and something dies, I lose, I'll lose whole samples. So and then they're randomized. So it's 2, 6, 1, 4, 5, 8, 7, 3, 4, and then we go. Yeah. So man, is this all 24? I guess it is. And then in this second block, it's 4, 8, 6, 1. It's a different order, right? So that's blocking and randomization. It's exactly what we want to see. We would be happy seeing this in the data for what it's going to help us with in MS Stats. Okay, so now let's go to refine, reintegrate. This is the peak scoring model, the mProfit, custom built scoring model that's getting used. It's not just Skyline's default scoring model. Let's go ahead you just drop down, say edit current, and we can get a really detailed look at what we looked at in the log. It was nice that we saw in the log what was, we could see sort of what the percentages were and stuff, but frequently we want to come in here and look at the model itself to be more confident about it. So, and are Agilent raw files supported? Yes, they are. Agilent totally supported. Yes. Is it possible to use DDA data processing, mascot.dat or other processes? Yeah. So we have yet to have somebody contact us about a DDA search engine that so people will contact us and say, hey, I noticed that I can't do Morpheus or something. Like, people are creating new search engines, and when they contact us, we say, give us some sample data, and we invariably make Skyline support them. So Skyline supports like 20 different search engines, and Mascot and MaxQuant are definitely popular among them. So, and you can get the full list on the Skyline website. So it actually turns out it's not this negative contribution. This red, yeah, so that's interesting that we should put something that into the log that sort of is parallel with this red thing. So this is just saying like, hey, we don't expect mass error to be a positive thing. So that's what's saying, and that definitely gives us some insight that there's some mass error issues in this data. And yeah, it's saying that like, hey, we're going to put a little teeny bit of weight on mass error because it looks like the decoys have less mass error than the targets. And that's just because, the targets are systematically drifting away and the random decoys seem to be, picked up somewhat closer to these things. We can actually look at the decoy mass errors after this in a second. But yeah, so intensity, all of these things are positive. This is the model, so you can see that there's good separation. You can see that behind here is a normal distribution, and that the decoys are actually fairly well, fit the normal distribution reasonably well. So our model isn't like producing, this is not a normal distribution, but this is, there's some stuff here that's like pretty much like the decoys, and then we get this stuff out here that's, systematically different from the decoys. And you can look at each separate feature, and you can see that, yeah, okay, intensity is maybe separating these things a little bit. Retention time difference, these can never be less than 0. So, it's harder to see that retention time difference is providing some separation, but it obviously is, because we have some percentage. And then the library dot product is always, or there's something really broken if library dot product isn't like above 10, 15, and we usually expect to see it above 20. So that makes us feel pretty good. Yeah, so these are, and then you could look at the distribution of p values and q values, and so you can really get a lot of insight into these things. I think we could also have a look at the default model. Would that work? Yeah, it's gonna recalculate. So this is Skyline's internal default model, which the thing about the mProfit model is that it trains the scores to be as effective at separating things as possible. Skyline's default model works pretty well. And identified count. So it identified count is for DDA data where you have an actual identifications. And now if we do train model, this is really only just adjusting the weights to make the decoys a unit normal, so that we get okay, so we'll go back to the script. So we want the decoys to be a unit normal, so that whenever we see a score, that tells us how good it is. So a score above 2 means it's like, well, it's what would, I don't know, 99th percentile. We want like a 99th percentile score, and above 2 is pretty close to that. So, so this is the Skyline default score. It does pretty well too. But obviously the mProfit score is, you know, usually better. And so we use it a lot. Okay, so that's that. I'm gonna actually, we're in an hour and a half. I'm gonna take a break, 15-minute break, everybody. Let me just quickly answer the questions that are here, and then we're gonna have a 15-minute break. So 2 minutes for answering questions, and then we'll come back and we'll discuss, you know, what more do we want to do. I've shown you sort of the troubleshooting, the main troubleshooting things that I would do aside from just actually looking at some chromatograms. And then, oh, but actually there's even a couple more places to look, which you can look right after. But eventually we'll decide, do we want to go on and look at the CelebSec data, or do we want to just stay on the Bruder data? Because that's a choice. Are recordings of all training sessions going to be made available? The answer to that is yes. We have to do this exercise manually through 1 by 1 peptides. Sorry for the typing error earlier. No, you don't have to look at anything 1 by 1 or manually, but we do highly recommend that you look at your, like if you just, that was the point, a big point that Lindsay made on the first day, I made on the second day. If you don't ever look at your data, and especially, right, so let's go back to here where we had volcano plots. You know, we'd said, wow, look at all these things. So we could now go, okay, great. One of the really different ones is P0267. So suppose I want to write a paper saying like, boy, these proteins were so incredibly indicative of the, you know, suppose I was comparing, you know, cancer cases to non-cancer cases, and I wanted to make these are probably biomarkers. So at this point, I have a set of, you know, I looked at thousands of proteins, but I have statistics that are telling me, boy, these are the things that are interesting. Before I run and write a paper about it, I really think I should look at so P02672. So you can go find P02672, and there it is. And you know, right now we're looking at the retention times. We can see how many peptides is that based on? Wow, lots of peptides. So we like that. You know, if we saw this was a single peptide, we might be a little bit more worried. Next thing we'd like to do is peak area replicant comparison. And then now we can see, you know, now we can see that there is quite some difference in all these things, and definitely appear to be varying at the same time. And we want to switch our order back to document order, because that'll put it in replicate order. And yeah, you can see like, wow, at sample 8, there's very little of this thing. And as I get, so I think sample 1 is the first in time. I don't know the data well enough to say like which one, you know, which one has the most osmotic shock time. I wish somebody who was here. But anyway, but yeah, so now I could be like, oh, wow, look at this. This is, you know, I really believe that this is an important protein for differentiating between sample 7 or sample 8 and sample 1. Because then I could look at each thing individually and go like, well, you know, how are these things? But the more I've looked at the underlying data, and you can see that this is just really nice data. You know, the more I've looked at the data, the more I can confirm. And we do definitely get letters from people going like, wow, this, you know, saved me. I was ready to say that X was happening, and then I looked at the data and realized that it was not happening. So, you know, before you make your conclusions, you definitely want to check. But yeah, so this is that, you know, you don't have to go to through each one individually. You can run statistics, and the statistics, the point of the statistics are your data is noisy. There's no way you're going to get rid of all the noise in your data, even if you went through everything manually. And the point of the statistics is to find the signal in the noise that you're interested in. And then Skyline is a great tool for assessing, you know, whether were the statistics right? And I think we just said, yeah, boy, we really think the statistics did a great job on pulling out P02672. So that's done. And Ali maybe is telling me to take a break or something. I don't know. Ali, you can talk. Was there something you wanted to tell me?
Yeah, I had the instructions for running the Skyline batch brooder configurations, and I was just wondering if that's something that I could share with the attendees this year, since a lot of people weren't able to finish that processing.
Yeah, I mean, you can put it in the you can put it in the group chat. So for everybody, another thing is that is it different from, so if we go to this has a lot of information, including following instructions for reprocessing brooder data with Skyline batch PDF. Is that what you were?
No, this was the PDF that I created after the May Institute session last year in response to some people's questions.
Oh, okay, sure. Yeah, like so we can definitely put that. So here is, these are the documents for the classes, and we can definitely put that here. Do you have permissions for this that you could just?
I don't, but I will make sure that it's up
yeah.
there, and I will send it in the chat now.
Okay, we'll put it up, and I'll put it, you know, these things are coming from my Google Drive. I have a Google Drive folder where I'm putting slides and presentations and the polls and everything, and we'll add those instructions there too. So reprocessing instructions, and I will get with Ali and make sure that's a live link to her instructions. So thanks for that. Okay, I'm going to take a break, 10 minutes. I'll be back at 9:45. Thanks, everybody. All right, well, hopefully some people are back. I think this is a really great question. So I was typing an answer, but I think I'm going to answer it live. It says, we do volcano plot before curation for biomarker examples. So I was like, whoa, we're doing a volcano plot before we've actually even really looked at the data. And that's what our processing did. And that's what a lot of other processing tools do that don't offer as thorough curation and visualization as Skyline. Just run through and then provide a volcano plot, and that's valid. You can get statistics out of that. We're going to be talking about how to improve your data even on a large scale with refinement, but it is valid to look for signal, right? So you always have noisy data. It's valid to look for signal in high noise data, low, and your goal is, we think you're going to get more signal if you can reduce the noise in your data. But yeah, like you certainly, there's nobody on Earth who's going to go through 50,000 peptides and curate them all by hand. So you've got to narrow down to some things you think you might be interested in, and doing first, high level statistical analysis, and go like, oh yeah, here's 20 things I think I'm interested in, and I'm not going to worry about, certainly the vast majority of these peptides aren't changing at all. And so like to curate them really thoroughly is a waste of your time. So yes, you can, I think people see everything that Skyline allows and say, you're asking me to do all this for every peptide. I can't possibly do it for 50,000 peptides. And it's like, no, we're not asking you, like we're asking you again to use directed investigation. So you use statistics to figure out what you want to look at, and then go look at it really closely and make sure that you still believe what you thought you saw. So that's a great question. Okay, so where were we? We were looking at all these differences. We've looked at the volcano plots. I do actually want to, I guess, before we just keep looking at the data, I guess I'm going to have some way of two participants raised hand. What's the raised hand? If you have a question, I think at this point, since people can't just talk, you have to put the questions into the Q&A or into the chat. Ali and Deanna, are you still there? Oh.
Yep.
Hello. Sorry. Okay. I was probably very, very light. Okay, good. I looked at the chat. It says, please use the headphones. I'm using the headphones. Hopefully everything's better. Voice is low. Yeah, okay. So that's what everybody was. So I added the instructions that Ali was talking about to yesterday's page. People are saying things are better. Okay, good. Thanks for that. Okay, so let's keep going. And I hopefully my TAs are still around, but I don't know, because they can talk and tell me that I can't be heard. Okay, so I do want to present a few more slides. I'm going to switch away from this computer for a second and present some slides, because there is this second data set, which we have full instructions for, and maybe we want to leave it at that, but I do want to explain it because it's going to be something that we're going to talk about in next week with Mina. And so I encourage everybody to come back next week. There are a couple interesting lectures if you're interested in this stuff. But we will talk more about this CelebSec data because it gave us the opportunity. So this is the experiment that we just looked at brooder. We talked about how there are these quantitative samples. We run DIA on all of them. You know, and in fact, we ran multiple replicates on every quantitative sample, so that we actually only had 8 samples and we did 24 runs. And that was all done in DIA. And I can't really tell you whether that was the DIA was done before the DDA, but then at some point, either before or after, we ran DDA on pooled sample and created this library, which was summarized in the CSV file that we imported. So that was the setup of the experiment that we just have been looking at, and we may go back to looking at. And at the same time, same year, so this is MCP 2015, also MCP 2015, there's this Selevsek et al. Paper, and they took a different approach. And there was some back and forth about, what was the right way to go for a while between the Aebersold lab and Biognosis. I think that a lot of people have decided that going with larger libraries is beneficial, but at that time, so we still have the same N quantitative samples that we run, and so over here on the left is just the same, but on the right, what they did was pooled the samples and then did some chemical fractionation, and then ran DDA on all those chemical fractions. There's like 42 separated samples. They're not all, before we ran multiple runs of DDA on a single sample. It was like, we did replicate runs of DDA on the single sample, but in this case, we actually did some sort of sample prep that fractionated them by size of protein or some sort of chemical separation of the proteins, and then digested them and did DDA on them. So the idea is that, we're hoping to get better coverage of all of the possible proteins in the sample, because we get, in each fraction, we've gotten rid of some of the really high signal proteins. So then we build this, what we would call a proteome-wide library, and then using a search engine, build a library. And I've done this I've repeated with Skyline. I can show you in a moment. We put up all that data, the PepXML and MZXML from the search that you could build your own library from, and I did that. So, but then also when approaching one of these papers and you're like, I want to reprocess the information from this paper, it's important to read the methods very carefully. So, and I have read the methods very carefully and tried to just totally reproduce what they did, and then go back and say, well, how would I change this? So there's, they use semi-triptych digest. There's an option in Skyline now to do a semi-triptych digest. When I processed, in subsequent processing of this, I got rid of the semi-triptych peptides. It just adds a whole lot of extra things to look at. I believe Ludovic Gillet, who was a co-author on this paper, when he says that, hey, some of those semi-triptych peptides are really there, I'm just not sure, how helpful they are for us to do the quantification we're interested in. And then they allowed up to 2 miscleavages. That's a setting in Skyline that I think we set that 2 miscleavages with the Bruder data as well. Carbamide methylation, that's pretty common. The carbamide methylation on cysteine, and then oxidation on methionine. I should have highlighted the methionine, but and then they ran Sequest and Mascot searches and used this tool called iProfit to produce PepXML. So in fact, when they published the paper, they didn't include the PepXML. They didn't include all the files to build the library, but I requested them, and they're now up on the folder, the Selevsek folder. So, and then going further, they chose an iProfit probability cutoff of 0.0242 to get a 1% false discovery rate, 1% false discovery rate at the PSM level. And now an iProfit score is not a false discovery rate. So they somehow, outside of of this, they decided, hey, 1% false discovery rate is when the I-profit score is 0.02, but I-profit score is best when it's like 0.9, sort of like, yeah, so 0.9 is a good I-profit score. It means that when you reach 0.9 with the I-profit score, it means that out of every 10 things you take, 9 of them are true, and 1 of them is a false discovery. So if you're using this low an I-profit score for false discovery rate, it basically means you have such good data that you just have to throw in a whole bunch of false discoveries to get up to 1%, right? Because at this point, out of every 100 peptides I'm taking, 98% of them are wrong. And so I was just like, well, that's crazy. I'm not doing that. So I use an I-profit cutoff of 0.9. So I'm like, I don't even want to go down to 0.5 where every out of every 2 it's false. I don't want a whole lot of false things. But I think in this paper they were trying to get big numbers. Big numbers is a thing that we like to show in proteomics, but I don't think it's necessarily going to produce the most useful quantitative results. So I did not do that, but I read it carefully. And then what they ended up doing is take the top 3 to 4 most intense transitions for every singly or doubly charged precursor. So again, I think modern day and the swath paper itself says you should try to take 6. So we don't generally, even with DIA, go as low as 3. It maybe be 4 to 6. And as yesterday, we were completely strict and said we wanted only things with 6. So this is a very permissive selection, and it's not what I would do later. But they got 330,000 transitions for 83,000 proteotypic precursors, and that's big numbers. Doesn't necessarily mean that's what you should do in your own research. And then another really important thing to note is that they ran 2 experiments, and I've already said this. They ran the quantitative experiment is osmotic shock over time. So it's a yeast experiment. This is the goal is to create a yeast proteome and analyze yeast. And so they do osmotic shock, I guess, which is simply introducing yeast to increasing concentrations of salt. And but before they did that, they just did a reproducibility experiment where they just measured their sample in replicate. So yeast digest in replicant to look at the consistency and reproducibility and of detection and quantification. And the paper actually says the N was 4, but when I got the data, I saw that there were 8 runs, and I asked them, what do you mean 4? You have 8 here. And they said we chose 4 because we felt it was more consistent with what people do because the goal was to measure CVs across the runs. And it's actually, CVs are systematically better if you go for small numbers of runs. So I think, again, this was, attempt. They're like, well, most people don't collect 8 things to do their CVs. There are a lot of people who do CVs across 3 things or 4 things. So they went with the industry standard, or the field standard, but it's not necessary. It's obviously better you're going to get more accurate CVs if you use all 8. So that's what we did here. So there's, to summarize again, there's a refinement experiment, which is a new thing. So I introduced you to how they built this big library and everything, but there's also this refinement experiment where, okay, this is the quantitative osmotic shock experiment here. And then they also do this reproducibility samples. So there's M of them, but it's a single pooled sample. And then they run M, which in this case is 8 DIA runs just on those. And then from that, we can do some bulk refinement. So we've talked about refinement, and I'll reintroduce it in a second. But we can either just use, well, and we can either just use this deep library straight on our quantitative samples, or we can gain some knowledge about what's measurable. You know, what's going to be measurable when we take it to this DIA. So we can take this library, pre-search it on just some reproducibility samples, and get some insight on how we're going to get less noise, right? So we can apply this library to these samples, and we're going to have lots more noise. And the question is, you know, if we could get rid of some of the noise, maybe we would get more signal. And then some people will argue like, well, but you're going to lose signal too. But you know, it's a trade-off. The less noise you have, the better you're going to be able to detect your signal. And yes, you do lose some signal sometimes. But so then again, reintroducing this concept of taking, you know, these just very broad things that we know, and putting them into a refinement cycle and coming out with a highly reproducible quantitative assay. And so our question is, can we do what, you know, a lot of that, what we've described as refinement requires really rigorous, you know, like ordering synthetic peptides and doing much more rigorous measurements. But can we do a little bit of refinement upfront and actually get a better quantitative assay than just asking about every peptide we know anything about? So that is, again, this is the targeted method refinement cycle that Skyline was designed to support for SRM. But what we're wanting to explore is whether or not we have to just ask our DIA data about everything that we could possibly measure, you know, in any setting, even chemically fractionated. And, you know, even now people are saying, hey, you could just use PROSIT to predict anything. And why not ask your samples about that? And so what we're saying is, yeah, it might make sense to, and we did this experiment with Skyline and Skyline batch to do this processing and end up with two different processings of the same data. And then we asked Mina and Olga to assess, like, okay, how do the data look to MS stats? You know, can you see that there's less noise? Did we lose important signal? But the refinement that we did is just looking at measurability and repeatability. That's what those 8 runs of just like everything's supposed to be constant in those runs. So that's our goal with the refinement. If you go and look at I'm going to go back to my work computer. If you go and look now at this is a fully processed CelebSec folder. You know, here's the osmotic shock data. Here are whoops, they're not in there. Okay, the data lives here. This is 16 files. These are the 8 runs of just totally replicates of pooled sample. And these are the 18 runs of osmotic shock data, which is a time course. Okay, so those 2 different experiments. And then we end up with 3 different processings that you saw the Skyline batch configurations for. One is just the way they did it for the paper, which is we just take everything in our library and we query it on the DIA data. And then we also take everything in our library and query it against the reps data, the replicate data. And then finally we have this, using the replicate data, we took only the things that we could detect in the replicate data and which we could detect at a low CV. And then we queried the osmotic shock data for that. So we have 2 configurations that query the osmotic shock data and 1 that queries the reps data. And then we use the query of the replicate data as a refinement. So then our goal was to ask Mina with MS stats, how do these 2 look? You know, does it look like there's better signal and lower noise, or what do you think? Because it was our attempt to just use large scale refinement you have to do one extra experiment, but then you can use large scale refinement. And we were doing that. We were already doing this in the McCoss lab on our own experiments. So I wanted to apply it to this thing that I found in the literature. So that is that. And now I guess I'm going to use the poll to ask, do people want to continue with the Bruder data, or, so I think there's a poll here, which is just, do you want to move on? So the question is, do you want to move on from Bruder? Like we're looking at Bruder data, we could continue to just explore it and learn how to use Skyline better with it, or we can move on to starting to look at the Selevsec data and how we set up. How did I close Skyline batch? How we set up Skyline batch so you can see in my Skyline batch, here are my 3 configurations. We could start looking, and 2 configurations run MS stats. So I do a low CV or an all. And next week with Mina, we will definitely look at, what was the effect of doing 1 round of refinement rather than just simply applying everything we knew, and trying to extract data for everything we knew out of the DIA. So we could start to look at that, which is a different data set. We could continue on this one. So I'm going to launch this poll, and if you want to move on to the next topic, say yes, and if you want to stay with Bruder, say no. There you go. But I think the poll is on. Okay, wow, everybody would like to go to Selevsec. That's it. Okay, let's do it. So yeah, that's pretty definitive. Sorry for the people who would like more time. I mean, this again, if you didn't get through the processing and you want to look at exactly the results I've just been showing, then you can go to the Bruder folder, and you could just download this 4 GB file and open it, and that would give you fully processed data just like this. So, but you can also put more effort into getting Skyline batch to run the data for you and have your own data set. But we're going to move on. I showed you a bunch of ways to assess these data and decide whether they're okay. And they are. This is really a nice data set, and we could spend all day looking at it and learning from it and how to use Skyline with it. So I'm going to close this though. All right, so I guess I'm going to go back to the poll, and well, okay, so I guess what I'm going to do is show you how these, so again, it's not totally normal that you would have these multiple configurations. Like Bruder has 2 configurations, and I'm doing that instructionally because it's useful for me to be able to just run everything but MS stats and then run MS stats afterwards, because MS stats takes so much longer than Skyline, and it also helps me be able to see run times and stuff. But so that's why we have 5 configurations, but we would definitely have 3 configurations for this experiment with the Selevsec data. So let's look at them. And so if we go to this one, the goal of this one is just to run the replicates and see how reproducible they are. And we can go ahead and open the results of that in a second. So, and again, that you can just do this. You should be able to just do this by bringing up the BCFG and then running it. And this is my, this is how I ran it. And there's no annotations file here because we're just doing these replicates. So this again says, like, here's the Skyline file up on Panorama. if we pop this up, you can see that, hey, it's this CelebSec panorama folder, which we can edit. And this is, again, the same kind of URL to a folder that we saw before. If we went to this URL, we would see the files for the that we would see this. So we're working on CelebSec. We would see these files. That's how we got that root location. So here are all the files for CelebSec. So that's that. Then we tell it, okay, we want to put the resulting analysis in this CelebSec reps folder. We've seen that. We're going to call the analysis file, synchronize it with the folder name. So we're, rather than just having CelebSec Sky in the analysis folder, we're going to have something called CelebSec reps.sky. And then the data directory is up here. You can see that actually there's some, last time we had just this, and this time we've got some subdirectories. So actually you can go into the raw files, and here you have WIF OS, WIF rep, and then DDA. And if you look at DDA, this contains all of the PEP XML and MZ XML for building the library. Oh, it's really slow. Maybe because all of you are downloading right now or something. I don't know, but I'll come back to that when it finishes. But yeah, this is going to show us the PEP XML and MZ XML that the library, that extensive library that they built, was built on. So, but here's what we have, and we want pretty much anything. I guess, Ali, are you on? Because I'm sort of wondering why do we have dot star here instead of just blank? But anyway.
I'm on. Dot star just includes all of the names in the folder, and it should be blank, and that is an improvement that should be made.
Okay. So I think that works. Let's see. So yeah, so I don't think that dot star is a regular expression that says anything, because yeah, so but I don't think we need it. It's optional. We don't need the regular expression. We'll get the same result with nothing in there. But so that's that. So then, and then here again is, we expect each replicate to match up to this, and this thing inside the parentheses is how we get the replicate name. So we're stripping off the ncelev underscore and the underscore SWE at the end, or the underscore SW at the end of the thing. So this is just defining what the replicate names are going to be. You could leave this is also blank, and then you would just get longer replicate names. Settings, again, we're adding decoy, shuffle. This is exactly the same settings we used on Brooder. And we would only use these settings at the top if we wanted to modify the mass accuracy or the retention time parameters. And then, interestingly, this is a very interesting aspect of this. We're defining, hey, we want to do a refinement, and from that refinement, we're going to end up with a new CelebSec low CV.sky, which is going to be a new template for us. We're putting it right in the root of our analysis folder. And in making that template, we're going to remove the decoys that we just added, and we're going to remove all the data. So we're not trying, we're on a template. We don't want data inside of it. This is a new thing we're creating. And we're saying that the minimum peptides for a protein, I think, proteins with fewer in this, so it's 1. So that's like, I guess that would remove things that end up with 0. So we're going to remove proteins that end up with 0 peptides. But we could make this too. We could make this something more strict. And let's see. And then let's see. We've also said we want the maximum precursor only. So that's a refinement, right? If we have peptides in our document that have the measured charge 2 and charge 3, and we're saying, hey, we only want, either charge 2 or charge 3. Just give us the one that's more intense. And then we're also forcing things to be above a 20% CV cutoff. That means across all 8 runs, we would like to see just the things, so what's going to go into our template are just the things that we can measure really reproducibly. The more variance we have, and this is technical variance, the more technical variance we have, the less likely we are to see biological variance, right? So our technical variance has to be sort of low enough for us to be able to see biological variance. And there's lots of reasons why peptides might have really poor technical variance, lots of it. And we went over some of them yesterday, like there could be issues with digestion, issues with the peptide degrading or sticking to the side of the sample vial, or there's various reasons that peptides are not well measured. And we're going to apply equalized medians to the global CV, because that'll give us a better median distribution. And we're going to also apply a Q value cutoff for detection. So we want to make sure that these things were actually detected at a 1% false discovery rate and in a minimum of 4 of the files. So we're not no fair getting a 20% CV if you're only detected in two of the files. And we could put that to, if we wanted even higher quality data, we could say, yeah, we don't care about you unless you're detected in all 8 of the files. We can put that as high as that. And then I think I'm going to look for it. So another one that got asked yesterday is, can I choose, a maximum number of peptides per protein? So maybe you say, hey, I only want the best 5. Somebody asked that question. How would I get only the best 5 peptides for each protein, or best 3 peptides for each protein? I think that it's possible to based on, so refining targets, so it should be in this list. Based on the imported results, we peptide peak rank, maximum peptide peak rank. So we could say, hey, maximum peptide peak rank is 3, and then we would get all of our proteins would get only 3 peptides, and we could say 5. So there's quite a bit of, there's quite a number of things that we could be doing here in this round of refinement, completely automated. We're not going to have to look at the document or do anything, and Skyline will automatically do these. And we haven't even gone as far as you might go, right? So another thing I thought of based on the question yesterday is, hey, we could just put 5 in there, and now we're only going to get, maximum of 5 peptides per protein. And we could have said, hey, at this first round, we're going to look at 10 transitions, and then we're going to pick our best 6 transitions based on the data that we see in DIA. So we're choosing our transitions based on DDA. We could also, so we could have done like this. Say, oh yeah, we're going to, choose our peptides and our transitions based on how they rank in the DIA data, but we didn't. So lots of stuff that can be done here. Just simply the concept to get into your mind is that we used an experiment where all we did was measure the peptides in replicate to get some insight in what the technical variance is like before we then go query all of our data with, just looking for everything. Because that technical variance is going to become noise when we're trying to look for biological variance, right? And then even here, we export a report and we run this little R script. This is a custom R script that I wrote myself that gives me some insights into detections. And so I decided to include it here. A bunch of what this does has since been included, like this actually maybe even analyzes the mass errors. And, there's a bunch of the stuff that this does has been integrated into Skyline. And I'll show you that in just a second. So, and then this is Skyline. So that's that one. And then we have low CV. So that low CV one, again, it's got, it exports the MS Stats input plus report, and but it doesn't run MS Stats. That's a separate configuration that runs MS Stats. But you can see that its template path is this low CV Sky. So that's the one that we generated in the prior. It's not downloading it from Panorama. It's using the refinement that we did with the prior configuration. And that's, and then now we're analyzing the data in the OS directory. We have some annotations because we want to annotate the bioreplicate and the condition. And settings are the same, no refinements anymore. And then we export the report. And then finally, all is really ends up looking a lot like the reps configuration, with the only difference being that now we're using the OS data, the osmotic shock data. So yeah, you can see that these would be fairly easy to create just by using this copy button. You create the first one, copy, and then create the second one, copy, and create the third one. And they're just slight tweaks on each other. But that's the processing. I have completed that processing. And so I would recommend that you can get this simply by, I'll go ahead and delete mine, right? So if I were just like yesterday, then I can get that back by going to the SelevSec folder and downloading the BCFG file. I click there, and then when I open the BCFG file in MS Stats, it's going to say, well, where do you want to put your analysis? And I'm going to just put it back where I had it there. So it's this SelevSec folder. You could create your own SelevSec folder starting with an empty folder. Mine's full, and I click OK, and then I have all these things. And then what I would recommend is you start with just download the data files, download the files only. And if you don't have a whole lot of space, you could just even start with, hey, I want to do the replicate analysis, and you could download the data only. And then, maybe that'll take you overnight. I don't know, but and then you could sort of step by step. The next thing would be just to run everything for here. And then once you run some osmotic shock data, you may want to run these MS Stats things too. But you can play around with these 5 configurations and run them a bit at a time, or you can just, roll the dice and do them overnight. But that's what the processing is. Let's go now look at the results. I do want to point out that there are there's a bunch of other controls that we haven't gotten into. If you wanted to create your own BCFG file, you'd click this share thing. And so this would basically allow us to create a BCFG file that had this is how Ali created that file that we're all using. And then we're mostly importing them by, we have only been importing by opening them, but we could also click import and go to downloads and import any BCFG file. So we could, import that one again.
Brendan, next time you have a chance, there's a fair amount of questions.
A fair amount of questions. So let's pause for questions before we get into the data. We're still, we have not looked at any of this data in Skyline. Hopefully we still have some time, so we'll get a chance to look at least the replicate data set. All right, so I'll go to the bottom because those are going to be the most relevant, right? When you run MS Stats batch, after running the batch without MS Stats, do you run all or RScript only? I typically run RScript only. Yeah, so that's a really good point. So if I go like this, So I've run all these things. Skyline's all processed. I will typically just say, hey, run our scripts only. And these are a bunch of, I used these all the time in my batch scripts. I'd be like, oh, I just want to export the report, or like, I'm going to start from exporting the report. I don't want Skyline, because Skyline will try to be smart about skipping work it's already done. Or Skyline batch will try to be smart about skipping work it's already done. I don't know. I'm not positive that if you ran all, it wouldn't start save over the top of your file and start re-importing. I don't know the answer to that one, or whether running all would actually skip the work that it's already been done. But yes,
I can answer that really quickly. Running all only skips the downloaded files that have already been downloaded completely.
Okay.
Everything else it does fresh.
Okay, so there you go. So yeah, yes, when you want to just run MS stats, that's one of the reasons this is you just click, hey, I just want to run the R scripts only. And similarly, you might, so suppose you wanted to do some manual curations correction, and you wanted to rerun MS stats based on it. You might open up the Skyline document, work with it, and then go, hey, start from export report. Right? That's you're just like, I don't want you to copy the template and re-import the data. I want you to use the Skyline document that I've got on disk. Suppose you went to that volcano plot and you just found, boy, that, I want to use one of those volcano plots in my paper, but one of the proteins that it's choosing is just garbage. It was one peptide and it's, and it's noise, and I'm just going to delete that whole protein, and then I want to rerun MS stats so that I get a really nice volcano plot for my poster or my paper. So that's another thing is, just start from, I just want to export the report again. I did that all the time. Like, it's like, yep, I've got processed files there, or there's for some reason MS stats failed, and I had to go figure out, why did it fail? Oh, I see, I need to change my script. Then you might find yourself doing a lot of run R script only. All right, so let's go. So the other thing I will point out is that there are the handy things to actually open the template file. So we could, we could probably, I guess we could do that for this. Does that work? Yeah, so this opens the template file for my processing. The problem is that I move my processing, so my processing is not, so yeah, I think I will move it back. So this is a template file, no data imported. We built a custom library. You can go view spectral libraries and have a look at the entire library and see that there's 84,000 precursors. And you can see that Skyline is not matching some of them for various reasons. But that just means that the settings aren't set up to match those, and they may be outside the range, the size that they look kind of small, so they may be outside the size that we're measuring here and stuff. But yeah, so that's the template file. You could certainly go, oh, I'm going to look at all the settings. Oh yeah, 2 miscleavages. That's what we talked about. 70 to 45 is the length I'm allowing. Here's the library modifications. Yeah, I'm not allowing water loss or ammonia loss, just oxidation and methionine. And so yeah, you can open up this template and get a sense of what's there. I'm going to close it back down, and then I'm going to actually go here, and since we're going to work with the process data, I'm going to call this select template, and I'm going to, so magically everything is going to now look like it's been processed. This is the process folder, and we can dig around in here, but there are some nice shortcuts here. And what I want to look at next, so I looked at the template file, I want to look at the results file. Or I can even just get back to that folder, the folder I was just looking at. Or no, this is the reps folder. So I could get in here and I could go, oh, here's the results of my R script. Before we open up Skyline, let's take, so this is my exported report. This is not MS stats. This is quicker to run, so I just run it. I don't have a separate configuration for it, but you can see what was my what was this R script I wrote, and I wrote this detections by run. So for both peptides and precursors, so I wrote this plot. This is an R script, and we then integrated this into Skyline. I'm going to show you in Skyline you can do this as well, but it gives you a sense of like, how many things were detected in, we're detecting a very similar number of like 18 to about 19,000 peptides in every run. And then, but if we were detecting the same 19 in every one, this would have just like this yellow line would be straight across. And then this blue line, which says what are the things that have been detected in all of the runs so far, would also be straight, very close to this median line. So that's what that plot is. You're going to see that in Skyline. It's very easy to get to in Skyline. You don't need to run an R script. Here's another way of looking at the detections. We expect a lot of things to be up at, so we can see that there's like 15,000, 14,000 or so that are detected in all 8 runs. And we said that our cutoff is going to be, it's got to be in at least 4 runs. So that's all the things in here. So we get like another 1,000 to 2,000 more peptides for 7, 6, and 5. And then we see, here's the other, and we see it actually kind of go up. And that's an indication that we have sort of false discovery rate accumulation. If this goes up on this side, that there's a lot of things that are getting detected in one run, then that means that we're sort of sprinkling these false discoveries over a whole bunch of runs. And if we ran 100 of these runs, we would get more and more false discovery rate accumulation. And that's something that mostly happens when we use these proteome wide searches. So it's not going to happen if we use a sample specific library like the one we did for Bruder. But it may happen when we just look at everything proteome wide. We'll start to just randomly see things sprinkled in every run. And then I also, these are CV histograms, plots we also imported, we added into Skyline, and it's saying like, hey, this is the CV histogram. Of the things that I found in all 8 runs, the median CV, 92% of my things of that kind were measurable below 22%. And here's the, you can see the median is below 10. So, and we now have these plots in Skyline. And if we go all the way down to the bottom, we see these are, CVs by intensity. So you can see that there is, the higher intensity things have better CVs. Basically what that's telling us. So a bunch of different plots, which I think all of these you can get in Skyline. But you can see that I just wrote these R scripts. You can write R scripts you can export data out of Skyline in reports, write R scripts, and have Skyline Batch automatically run them for you. So let's go back to Skyline Batch, and now we're going to actually click on the hey, show me the results button, and it's going to import into Skyline. Okay, so let's see. Questions. Here, when we remove decoy, remove data, does this mean remove proteins with less than 2 peptides if we use 2 peptides in the refine window? Yeah, if in the refinement settings you said, so here's our reps. This is the configuration where we're doing refinement. And if we go in here and we say minimum peptides 2, then we could remove all proteins that don't have at least 2 peptides that meet our criteria. I decided not to do this because the criteria are pretty stringent already with the CVs and the Q value cutoff. So we would just have even fewer things to look at if we went with a 2 minimum peptides, but we could do that. And again, you can, so there's a bunch of controls that you can do in creating your low CV document. And so first we're going to let's look at the results, and then we can look at what the low CV document looks like. I can see my video has frozen again. I don't know what's going on with that. Okay, so we open the document. Answer live, done. Could someone explain how Skyline batch distinguishes technical CVs from biological variation? So the reason we know that this is technical variation, right, is that these are just technical replicates. So Skyline, so we did it's not nothing special that Skyline batch is doing. It's just that we did or not we, I'd say the Selevsek, Ludovic Gillet, and Natalie Selevsek did an experiment that captured only technical variation. And so we can use that experiment to decide, hey, let's get rid of some stuff that has a lot of technical variation that we can't detect well, before we start asking MS stats to tell us what's changing based on the osmotic shock. So what we want to detect is biological variance. We want to detect variance when we introduce a lot of salt to our yeast, and we could just go, hey, go look for everything. Or we could do refinement, and we can do quite a lot of refinement, but we're just like, here's a broad kind of refinement where we just do technical replicates, and then we decide what can we measure consistently. So that's this thing. I guess we could take a look at some mass errors. I think we're a little early to be looking at it at an individual level. And then I have the 2D histogram here, but I'm going to go to the 1D histogram. So again, just detecting sort of like, okay, what's the quality of our data? We can go through the same sorts of things that we went through before. Wow, this is much more like what we'd like to see. The mean is 0 and the standard deviation is 2. Like, this is what I said was, I would love to see a standard deviation of 1, but I rarely do. So this is a well-calibrated instrument and this is a triple TOF. Let's go with, so see, now we're looking at replicates single, but we have 8. So let's see, does it change much? Not really, so all 8 runs were done with a mean mass error of 0.1, so right around 0, and a standard deviation of 2. So I would say, you can see it going out past plus or minus 10. Let's go see what the settings were. But I would say you should feel comfortable using a mass error tolerance in the transition settings of 10 in this case, because the data is so good. Hello? Okay. So, on the other hand, this we're using profile extraction from TOF data. So anyway, so we used an 18,000 resolving power, and we used high selectivity extraction. And this is an older triple TOF even, but yeah. So anyway, the mass error looks really good. If we were using centroided data, we could use a 10 ppm mass error, but we're not. But yeah, so we see no problems with mass error here. It looks great. And we can just close down all these mass error windows. Here is the retention times. And if we can order by acquired time to make sure it's already an acquired time. So, these are, there's some changes in retention times, but, I think not really a huge deal. Maybe we should go to all to get the top-down peaks. So that's really nice. When the peaks all overlap, I usually feel pretty good about that. And then, we could look at the refine, reintegrate, and look at the scoring model. And again, we can, if we're doing this in Skyline batch, we could have gotten some insight on the scoring model from the log. Could someone explain distinguished CVs? Yeah, I answered that one. So is adding the R scripts in the reports of Skyline batch how we could say analyze many fractions as a batch? Yeah, absolutely. You could, yeah, you can write you can have very complex R scripts getting executed, and memstats is a very complicated R scripts, but you can, if you know how to code R, or somebody on your team is really good with R, you can create R scripts that will analyze your data. Skyline's really good at exporting tabular data, and you can get insights into a lot of things. And pretty much any value you see graphed here, you could export in a report. So here it is. So this is one of these intensities where the intensity is actually a bad thing. And that really starts to happen when we have lots and lots of decoys. And you can see that rather than just having that, the targets no longer look like just one distribution that we're trying to separate from the decoys. And that's because this isn't a sample specific library. We didn't do a DDA experiment on our sample. We did it on this highly fractionated set of samples to try to get as many things that we might see in our sample. So we don't know ahead of time what we're going to see in our sample. So there's lots of stuff that's just, mProfit is telling me, yeah, this stuff is not in your sample. And so in this case, when you have that much stuff and that little prior knowledge of what you're going to see, intensity actually becomes, more intensity is worse. So we might, and if you decided, I don't really like that, I'm gonna I don't think I don't think it's ever helping your model to have a score that's going against common sense. So you could definitely remove it and retrain the model. We don't, but it's also so little impact that we probably don't need to do that. Retention time difference is better here, and we'll take a look at the retention times in a second. This is approaching 10%, which means that the retention time prediction is pretty strong indicator. Library intensity dot product, again, I'd say I almost always want to see it above 15 to 20. And then the shape score in this case, it turns out to be pretty good. And actually, a lot of these scores are, and mass error, as we said, the mass errors are really good. And so that then becomes a strong score. So this is how mProfit really shines, is that it can adjust the scores based on the data. Whereas, again, we can look at the default training model, which I think will do okay, but it doesn't adapt at all. It's just like it's a set of scores, and it now forms the seed score for mProfit. So so again, all it's done, and you can see that it does not get as good separation as the mProfit score, but certainly it is getting some separation. And it's giving weight to the same scores that we, well, it's giving similar weights. So you can see that these are fixed, these are actually fixed weights that are getting scaled to make the decoys a certain shape. But you can see the percent contribution, the library is contributing less. We're not using the mass error at all, which turns out to be pretty good here. But otherwise you can see that they're fairly similar scores, I think, to what we saw. Okay, so let's go take a look at, so we looked at the mass errors, we looked at the model looks good, the mass errors look good, and I would say we almost always also want to have some insight into the retention times and the regression, the score to run regression thing that shows us how the IRTs did at predicting where the peaks are. So I will grab this. And so we're already looking at the residuals, and yeah, I don't know what's going on with these ones that are way out there. That's like not even, I don't quite understand what that means. Because we picked, let's see, what was our settings? Transition settings. So I think we're plus or minus 5 again. So we, nothing's getting very close to 5. I mean, there is stuff out to 5, but things are really clustered. We don't see, except for this tail over here, we don't see, anything but sort of randomness. And then I think, let's see, do we have points? So if we do 1% FDR, so again, remember that these data have a lot of things that were not detected, right? So it looked like almost half of our things, couldn't be detected in this thing. And that's really, that alone is really, if all we did in refinement is throw out things that weren't detected in at least one run, that would be a good idea. Like, it's really unlikely that we're going to find some biologically interesting thing in something that was not detectable in a replicate run like this. And you can, you're really gambling and hoping if you go that way. But yeah, so now you can see that we get much tighter around 0. And yeah, the bulk of our detections are within a minute, and certainly within 2 minutes. And so you can see why retention time becomes a much more powerful score than it was last time. So yeah, so again, this all looks really nice. And then we can actually, I promised you, so you've seen the mass errors histogram. Okay, so I promised you that some of those detection plots and peak areas. So let's go. So now we can look at the CV histogram. So I said that those plots that I showed you generated in R are now frequently, when we come up with some really useful way of looking at the data, we try to get it into Skyline. So let's look at the CV histogram. So this is the CV histogram, and again, this is without any cutoff. This is showing me all the targets and their CVs, and there's this bump out here, which I'm going to tell you is likely things that are just, they're not really what we're trying to detect. They're just random stuff, and they have very high CVs. So we can go to, actually in this case we have to go to properties, and we tell it we want a Q value cutoff of 0.01. And then we can click OK. And now it's applied the cutoff, and it's saying, hey, there have to be at least 2 detections. And we can play around with, like, well, what if it were just, it won't let us go down to 1. We can go, what if we want things that are only detected, in everything. Okay, our median CV is 0.8, and 92% of our things detected in all 8 runs are below 20% CV. We can choose a normalization method. The normalization method that we chose in our refinement is equalized medians. And so we can see it gets even maybe a little bit better, right? And then what we really did in the refinement was this 8.5%, and then like 90% of these things. And then, so this is the refinement we did, which is now you can do it manually inside Skyline through this plot by going remove above CV cutoff. And this now removes everything. And you see that there's a little bit left over, and that's because when we remove a whole lot of stuff, the median moves, and we're using median normalization. And so that's that weird artifact. If we weren't using median normalization and we did the remove, we would actually see everything disappear above the 20% cutoff. But that's what we did automatically in the refinement. It's like this. And then we would also then remove empty proteins, because there's a lot of empty proteins. But anyway, so that is the way that's the kind of refinement we did to get the low CV. Because of Skyline's multi-level undo, I can just undo that and get back to my other document. And so this is what we're looking at. So I'm going to close that. That's how you can visualize it really easily and interactively inside Skyline. You can try other normalization methods. This one does. In this case, is no other, but if you have heavy labeled peptides, or you have actually in our most recent version, I think you can try tick normalization here too. But anyway, so that's that. And then the last plot I want to show you for these data is to look at the detections. So these are actually the plots that I just showed you in the R PDF. So there really would be no reason to run that R script, except that I just wanted to demo how Skyline Batch runs R scripts. And maybe it's convenient to have that PDF lying around to look at. But here now you can see you can either see the detections at the peptide level or the precursor level. And those are different right now because some peptides have multiple precursors. And yeah, you can see again, here's the line showing you how many overall peptides are getting detected. And ideally, you would detect exactly the same peptides in every run, and this line would just be here. And this is showing, how many peptides are detected in all runs. And ideally, again, this would be, you're never losing peptides, but it's not. And this blue line is the number of peptides detected in 4 out of 8 runs. So that's the center of this. So that's that. And then we can also go to view detections and look at the histogram. And then this is exactly the histogram that was in the PDF. Again, we can see lots of things that are detected in all 8 runs, and descending down to, losing some in every run, but then also going back up here, which again, as I say is evidence of false discovery rate accumulation. So you're accumulating more and more stuff that's random because, every run has some false discoveries. So ideally, you wouldn't see this, and you don't see this with a sample specific library, and we won't see this when we look at the low CV data set either. If we were to take the low CV data and import it, we wouldn't see that tail and import these data. Okay, so I'm going to answer some questions. That's the replicate data. And our goal then is to produce this low CV document and then process the osmotic shock, which is a biological, has biological variants. And we're going to process it both with just like, hey, find everything, and then run that through MS Stats. And MS Stats, can you find anything interesting for me? Versus, hey, we're going to use these really high quality peptides. MS Stats, can you find useful signal in that less noisy data? Okay. On the IRT plot, what are the values on the horizontal axis? Let's bring that back up. View, retention times, regression, score to run. So if I am in this, I think what they're saying, I'm going to pop this out, make it as big as possible. So if you right click and plot the correlation, undo all zoom in pan. So that's an important thing to know. If you zoom in, Skyline will sometimes stick, and then you need to do undo all zoom in pan. So here you can see this is not the residuals, this is the, and then if you see things along the zero axis, those are things where we couldn't find we couldn't find anything. You might have had no signal, right? So you can click on them, right? You can click on any point. You can say, well, what is this one? Is that, do I really believe that? It's kind of not, it's pretty far away from where it's predicted. I'll put this back. And then it's like, yeah, well, look at that. That's a pretty good peak, you know? And I can, if I want to look at more peaks at a time, let's go view, arrange graphs. And I think if we did a groups of 6, oh no, we have 8. So let's do group by 4, and that, and tiled, and yeah, okay. So there, now we can look at it, and well, you know, I guess I'm not totally sure. We are picking out by 5 minutes every time. But I'm not that sure that we, you know, that based on the fact that let's go to view peak areas, replicate comparison. So this is something that Lindsay showed the first day, is if you right click and normalize to, oops, right click and normalize to total, you can get a sense of how consistent these are, and they're not very consistent. I would say, you know, this one and this one, which are the 2 that are showing, but then, so it seems like maybe there really is, maybe our peptide really is way out at the end, but we're losing it. So we would want a bigger retention time window to consistently get this thing, which does seem to have coelution on all of our, you know, it's just a single, in that case, it's just a single spike. But anyway, so that's what, you know, we could click on any one of these things, and you can certainly click on the ones that are down here. And typically they are, for some reasons, you know, like they could be that Skyline didn't even manage to extract a chromatogram for them, or they did extract chromatograms, but they ended up looking like, you know, just right along the, there was nothing, there was no signal at all. So that's that. What is the scoring model? What are the differences? So the scoring model is like, how does when faced with a chromatogram, how does Skyline decide that this is the peak? Yeah, you can definitely see some noise here. You can see some interference here. So like, if, again, this is like, you know, and this is one of the examples I showed in my slides on the first day, you can see that there's really obvious interference on the Y4. And so if I could curate all this, you know, everything, I would, you know, I would be going, yeah, I'm going to get rid of the Y4, right? You click on it, you get Skyline highlights it in red, and you get, yep, okay, I'm convinced it's the Y4. And now I would get better quantitative results if I had done things this way. And so you're just accepting, when you do this large scale processing, this is true of all the tools, you're accepting a certain amount of noise, and that you could get rid of if you could do everything manually, but you can't. So you just live with the noise, and the statistics, you know, I mean, that's still, there's a lot of signal that's outside that interference, and hopefully it, you know, what we get, and we see that very consistent measurement. This is probably a peptide that would get pulled forward to our next round. So, but yeah, okay. But the scoring model is just, we look at all these aspects of every single peak. So you can see anything that has a number and a mass error, that's something that Skyline identified as a peak. It was a candidate. So Skyline will pick 10 candidates in the set of chromatograms, and then a maximum of 10, and then it will score them, and it will say, okay, well, this is the one. you know, so it picks something, and we're actually adding a new grid to Skyline called the candidate peaks grid. So here you can go to other grids and you can see like the audit log, and we haven't even gotten into group comparisons, which is also really, and the results grid. There are all these grids are very useful. We're adding a candidate peaks grid, and that would show you, you know, when you bring it up, actually, if you go to view, we've looked at the document grid. If you go to results grid, it's going to show you document grid data about the currently selected thing. So as I select through here, you can see it's showing me the retention time. So so we're going to have something called the candidate peaks grid, which shows you the 10 peaks, you know, in these runs, and how it chose what it chose for the active one, and it will break it down. The model is just you take the scores and you multiply them times weights, and then Skyline picks the highest scoring peak. Long answer, sorry about that. But yeah, hopefully that gives you some information. There's a paper called mProfit that explains the mProfit way of doing things as well. Can Skyline report on how many data points a peak peptide has in the document grid? Yeah, so obviously I think we've shown you here. I'm gonna go to view auto zoom best peak, and you can see this little 24 here, 23. That's showing you how many points there were across this peak visually. And yes, you can go to the document grid, and it's a transition level thing. So if you might want to start with the transition, and you can see there's 600,000 transitions here, and there's but if you went to customize report and you double clicked on the fragment ion, that's a transition level thing. And then in the transition results is where you find all the statistics about the peaks and stuff like that. And there is cycle time across points across peak. So we give you both what's the cycle time, the distance, the average distance of these points across the peak, and the points across the peak. And this, because this is such a big document, this might take a really long time to show me, but I can add those. Okay. So I would definitely recommend for anybody, you know, like when you want to get to the next level of Skyline or the highest possible level of Skyline, you want to get very familiar with this document grid, because it's extremely powerful. And again, it can give you access to anything. It's also, you know, you can export the report from here, or if you go File, Export Report, we can now export that points across peak report as a CSV. So you can see it live here. You can also, and you can, you know, you can also you can also export it to a CSV and work with it in Excel. So let's go ahead. So cycle time seems to be pretty consistently about 3 seconds. And we can, let's just filter for, so you can get to this filter thing just by clicking on a header. And we can first filter for is less than, let's say, is there anything less than 8? You know, because 8, let's say 8's our minimum. And this, did that work? Is less than 8 filter type. Oh, it finally, okay. It took a little, yeah, boy, we need a little thing that so yeah, so there are actually 60,000 peaks out of nearly 5 million that have fewer than 8 points across the peak. And some of the 4 points across the peak, we might want to be, looking at and thinking about. And yeah, if we wanted to look at one, again, there's all these things are clickable. So let's say, okay, well, here's a 4, here's one with 4. I should be able to click it. Oh, this is a decoy. Ooh, I open up the decoys. So this is in the decoys. I guess I would probably want to also filter my report for decoys. But yeah, so this is something that has very few points across the peak. So yes, lots and lots. Again, like Excel, you can go very, very deep and do some amazing things. So boy, I don't even know where that one. Why does the x-axis go to -50? Which x-axis? What x-axis?
I think they're talking about the retention times score to run regression graph on the right.
Oh. So this is a score. And yeah, the IRT, the diagnosis team, I would do it differently. They chose to have, I think they were trying to make it be as similar as possible to SSR ArcCalc scores. But so they chose a certain peptide to make 0 and another one of their peptides. So if I go to points and say standards, you can see that, wow, the standards didn't do that well in this run. That's interesting. Because these are endogenous, so we're not using IRT standards. Okay, so yeah, so this is, but if we looked at the Bruder data, those are the diagnosis IRT standards, and you would see that one of them is around -20. So they just chose to, it's a range that they chose, and it's calibrated. Sometimes when you have things that are unscored, they'll show up even further to like -60 or something. So it's just that, yep, that's the reason it goes to negative is because this is a score. You don't see negative retention times because those are actually measured times. But that's the regression to, it's the scores that you see in settings, peptide settings, prediction, and you edit this thing. These are the scores, and you can see that the standard scores that we're calibrating to, a bunch of them are negative. So that's the answer to that one. Can you get retention time for each species in the table? Earlier peaks should be narrower. Can you get retention time? Yeah, I mean, I'm not quite sure what's being asked there, but in the refined window batch in the refined window in batch, how is the Q value calculated? So yeah, the Q value comes from the model you're using. So if you chose to use an M-profit model, then it's coming from this model. And if you want to get really detailed understanding of the Q values, there's a paper by Story Tim Sharani that explains it, and then you can certainly zoom into. We try to give as much detail in these plots as possible. So the scores are calculated using these weights, and then the best peak is picked, and then the p-values are calculated based on where the score is relative to this orange normal distribution. So we use the orange normal distribution becomes where you are on that distribution becomes your p-value, right? So if you're way out here, you could have a 0.0001 p-value. And if you're in the middle, you might have like a 0.5 p-value, or even way over here, you might have like a much higher p, like a 0.8 p-value. So that's how the p-values get calculated. And then once you have a set of p-values, then, well, this is this thing called the pi zero. So you can see where Skyline thinks the pi zero is. And you have to read the Story Tibshirani paper to understand this. And then using that pi zero, it converts the p-values to q-values, which are really just an adjusted p-value. So that's how it's all calculated. I think Skyline does some of the nicest job of any tool around. Of course, I think that to show you the details of how we get from these raw scores all the way to Q values. So if you want to dig into it, that's the place to look. Let's see. Okay, we are running to the end of our time. Boy, there's still quite a lot of questions. I'm going to stick around for the questions. I guess what I'm going to do quickly is just finally, let's go open. We won't save our changes. We're not trying to edit this file. But I'll quickly open the more refined of the two. Let's go to the low CV document. So you can see we're looking for 77,000. So if you look down here at the status bar on the bottom right, you can see we had 3,500 proteins, 77,000 peptides, 100,000 precursors. So our extensive library is really big. And then, if we go to SelevSec low CV, that's just the things that we think we have high confidence we can detect. And we're just analyzing those in, we're just looking for those in the osmotic shock data. And that's this data set. And you can see that we're now down to, hey, we're only looking for 25,000 peptides. And again, 25,000 precursors, because we only have one precursor per peptide mostly. And we've lost a bunch of proteins. We just don't think that we can, despite the fact that we could detect them in in fractionated data, we just don't think that we can detect them quantitatively in this sample prep. So, and then here you can see we now have all, I think, 18 runs, and this is what will get run through MS Stats, as will the other one, which the other one is running exactly the same file with 100,000 precursors against the osmotic shock data. And I'm gonna cut to the chase. There's going to be a lot more quantitative noise in the MS Stats analysis. And so that is where I will wrap up, aside from just staying around to finish up answering questions. I don't want to leave any questions unanswered, but everybody can certainly leave at this point. I hope you've gotten some insight in how to run these experiments, or how to run this processing, this stage of the processing. Play around with Skyline batch, the BCFG files, doing the processing yourself, understanding it, doing the DIA swath tutorial, which is, there are actually two pretty good tutorials right now. So, if you really want to become expert with DIA and Skyline, I would say that you should be doing this tutorial. This is the analysis of DIA swath. And then, potentially looking, there's some webinars here. And then there's also just basic data independent acquisition. This doesn't even really get into models. It's just like looking at DIA data, looking at the spectra, understanding all the windowing setup. So this is just, if you're setting up your own DI experiments, this gives you some really basic understanding before you get into all this stuff about models and stuff. But I think it would be an interesting exercise to go back and do this tutorial and this tutorial sort of runs you through this, building a library just the way, like, rather than using an assay library, here's the Irt peptides are getting calibrated, and you go all the way through this, and you could just do this same thing and go through this wizard, but only building a template. So don't import any data. Just stop here, with that, and don't ever tell Skyline about your files, and then use Skyline batch to process them. That would be a great exercise to get a sense of how we're saying you could use Skyline batch. So everybody's welcome to leave unless you want to hear answers to questions, and I will trail out a little bit longer answering questions that I've gotten behind on. Sorry about that. So should we process this data set for next week's Skyline part? I say yes, go for it. Like, I mean, again, at every stage, we're going to start up with something that you can download or you have. And next week, we're mostly going to be focused on the MS stats processing. And so all you would, we'll probably put up files that you could download and run through the MS stats processing without using Skyline batch. And those files are just going to be, all you need to do the MS stats processing is 3 files. And I used to just zip these up and give them to Mina to do the next section. So you need the MS stats input plus from the brooder processing, and in the SelevSec processing, you need from low CV, you need the MS stats input plus, and from the all, you need the MS stats. So those are 3 files to work with these data in MS stats. If you've actually run Skyline batch and the BCFG all the way to having these PDF files, then you're a step ahead, and you'll come in like, oh great, I'm just going to look at these results. I think it's likely that Mina will open up RStudio and start like showing you how to use MS stats from RStudio. So that's that. But yeah, I say keep going on the processing, keep going on the tutorials, especially if your goal is to learn about DIA. Can you post the QA for you today and yesterday? We will do our best. I'm not actually the owner of this presentation, or I think I would have gotten some sort of email saying like, hey, I should have gotten some sort of, or somebody, I think probably Olga is getting something that is like, here's the summary of what happened today. And I would expect that to contain the Q&A answering. So we'll do our best. We'll try to see if we can just snapshot stuff before we leave today. And yeah, thanks. All right, thanks. Yeah, QA logs. Okay, thanks for that. Where are missing values handled in Skyline or MS Stats? MS Stats handles missing values extensively. Skyline also, it's not as sophisticated. I think in general, it's assigning missing values. It's trying not to use missing values, so it's just excluding from the statistics. So you can see that here, Skyline is doing a volcano plot. So Skyline itself has this ability to define other grids group comparisons. You could add one here, or you could go to settings, document settings, and you can go to and define group comparisons. And so this is how you define a group comparison. Skyline does have some missing value handling in there, and you can set it up. But MS Stats is way more sophisticated, and there's a whole paper on it. So if you look for Mina Choi's MS Stats papers, there's one that talks about how it deals with missing values. But it's coming from a statistical lab, and it's I would say it's best of class. Okay, so anyway, I guess we did. So the low CV data was with a smaller target list. Yes, the low CV data is a smaller target list, right? It's our refined target list. We did a refinement that said, hey, we're not going to analyze anything in the DIA data, which when we throw out a whole bunch of stuff that we're not likely to detect, it improves our multiple hypothesis testing, and it improves our statistics because we don't have to say, yeah, we looked at 100,000 things. We say, no, we looked at 24,000 things. They're well targeted. They're things we're pretty sure we can measure, we can find. So, you know, going in, definitely what we were doing in the McCoss lab is this kind of refinement. And I proposed to Mina and Olga, hey, let's try some of this and see whether it improves MS stats handling. And I think you'll hear about that next week. So, but yes, the low CV is with the refined set of targets. The all and the reps were done with just everything in our library. Is there an optimization methodology built into Skyline? Yeah, I don't know. I'm not sure what you're asking. Optimization can mean a lot of things. There's lots of optimization. There's definitely collision energy optimization. There's parameter optimization built into Skyline, which is highly, you know, is well used and well liked by the targeted mass spec community working with triple quadrupoles. But I don't know what other, you know, what other optimization methodology. I'm not quite sure. I'm trying to import DDA data from Mascot and Skyline, but got nothing. It says it is missing raw files. Do they have to be included for the analysis? I'm gonna say, you know, you're working with your own data at this point. Post to the support board, and we will help you out. Yeah, that's the thing. Definitely Mascot works. You shouldn't need raw data to build a library from Mascot, but I'm not sure what exactly you're doing. So we gotta dig into that more, and the support board's the best way to do that. So okay, so then there's somebody who was just saying, so all the peak picking data we see in Skyline results is already 1% FDR based on scoring model. So that, no, actually you can see Skyline, you know, you can see every peak. You know, in this case, maybe these are all 1% FDR, but you can see even the bad picks. I guess it would be nice. We have in the spectral library, we've put a score up here. I guess it would be nice to be able, once we've got the Q values, to be able to put them here so that you could see, hey, this peak had this Q value. Again, we're also adding this new grid, which will allow you to see scores. But no, you can really see some terrible scores. And again, we could, let's see, we go to view document grid. And before we did points across the peak by transitions, we could also do, so that's still showing we could do a precursor plot, precursor grid, which, so that's the library score, but we could just do actually, I bet we have this report. So if we go to precursor peak areas scored, this plot has Q values. So I guess this is showing you, this is pivoted by the replicate name, and it's showing you the area and the Q value. And so, yeah, some of these Q values, like they look like big numbers, but they're actually small numbers. They're to the -8th. I think if we go to this report edit report, and we switch from annotation Q value to the actual detection Q value, I think that will be formatted better. So, because then we know it's a Q value. The annotation is the old way of doing things. So yeah, so here you can see lots of really low zeros, and we could find something with a high Q value, although this data has lots of things that are in low Q values. I'm going to go ahead, edit report, and I'm going to turn off the pivoting. And now I could find filter is greater than or equal to 0.05. So these are, wow, I guess it's finding almost everything because this is our low CV data. But I guess here's one. And we could say, yeah, this is, it's truncated. It may be the peak, but it's not a great peak. But we can still see it in Skyline. It's not filtered. But yeah, you can see now with all of our high CV things, we're finding things really well. And so this is going to end up being really clean data for MS Stats. Looks like, and then there are some bigger questions from Mark Wingard, and I'm not going to answer those. Let's see, what are you asking, Mark? Can you access the type of fragmentation? Oh yeah, NIST peptide fragment libraries. Okay, so yeah, so Mark, I think, is asking for us again to put more information. If we go to the document grid and we switch to replicates, or actually, yeah, replicate, or we just edit report, and then in replicates, he would like more information. Yes, we can put a whole bunch of instrument information. We've got the instrument serial number, we've got the acquired time, and we could have all kinds of information about what was in this file that we ran. So, and that would be helpful for people who are just reading a paper and trying to figure out what did they use. So thanks for that suggestion. So I'm going to get rid of those and still have one last. Let's see. Can we use Skyline to process SIM, selected ion monitoring data? Is it similar to MS1? Yes, you just set it up as if it were MS1, and Skyline. Actually, if you have SIM data, Skyline will prefer it. So you go to transitions. In the latest Skyline daily, because of some DDA data work we were doing. So here's, you would just go MS1, and then it's gonna do your SIM scans, and it will hopefully do them. It should do them well, and it will prefer them to the survey scans. And so in the latest version, because Thermo put SIM scans in that they just use for quality control, I've added a checkbox that says ignore SIM scans, so that we can extract from the survey scan even when SIM scans are present. But if so just read the MS1. If you're using SIM scans, read the MS1 filtering tutorials. All right, so that's it. I'm going to see if I can get all the answers and post them. But there's only 25 people left, and some of those probably are just people who walked away from their machine. So thanks very much to everybody, and yeah, keep coming to these, and I hope to see you next Tuesday for MS Stats with Mina. Bye. I guess some people are here. Thanks. Awesome. Thanks for hanging with us. All right. So How do we get this?
Brendan, if you're still trying to get the Q&A, I just copied and pasted it into a Word document. It's not like nicely formatted, but it has all the text.
All right, I'm going to take off. I think we can think the person to get these questions is Olga. But
Sounds good.
I think it's all captured. I think it's all captured.
Yeah, if it's not, just let me know because I have it in a Word doc.
Yeah. Okay, cool.
Okay.
Yeah, I mean, but Nat gets them every time. And I just signed into my Zoom portal and I don't see anything, even though I'm currently host of this thing.
Yeah.
It doesn't, it's not saving to my Zoom portal. So,
Makes
but yeah,
sense.
I'll try to hook up, cause yeah, Olga isn't doing it automatically for us. So, all
Mhm.
right, cool. Thanks, Allie. Thanks for coming.
Yeah, no
Helping
problem.
out. Yeah.
Yay, Skyline Batch.
Yeah, Skyline Batch. Have a great um rest of your term. And
Thank
yeah,
you.
are you coming back to Seattle at all or
I am, yeah, in the
yeah.
summer. For
Well,
summer.
come say hi. We'll have
Yeah.
coffee or something. Okay. Cool.